All right. Thanks everybody for reconvening this morning. I really enjoyed yesterday's presentation and discussions, lots of good perspectives. And I'm excited to hear the great lineups that we have set for today, their talks, as well as our breakout sessions. First of all, I just wanted to acknowledge the sponsors of the workshop and thank them for making this possible. So I wanted to say thanks to the National Science Foundation, Division of Atmospheric and Geospace Sciences, as well as the National Center for Atmospheric Research for supporting this workshop. They provided all the travel support to get you here, support for the coffee that we have out there as well, and a lot of the resources that we have available to bring this community and group together. So I appreciate their support, and this was supported as part of what's called the Innovations in Open Science program for planning workshops. Then I'm just going to skip through so we can review today's agenda. So we're going to have a plenary session this morning, very similar in structure to what we had yesterday, followed by a coffee break, breakout sessions, and assigned rooms. So hopefully most of you know where the rooms are now, but feel free to ask if you have any questions on those. Then we'll have lunch for the majority of the workshop on your own in the Mesa Lab Cafe. And then there's a subset of people that'll meet up for lunch in the Damon room, and you should have received an invitation if you're in that group. And then in the afternoon, we'll look at data producer needs for data curation and consulting services and follow the same structure. And a bus will depart to the Hilton Garden Inn at 5:30, and we'll make sure it's down at the bottom of the what they call the key area today. Please add suggestions. Once again, if you have suggestions for Friday topics that come to your mind or any questions in general, to the Slido link that is provided through these slides on the QR code, and I think I sent it out via email. But if you have a question where this link is, please feel free to ask. They're going to show it again here once I'm done with this slide deck of what we have up on Slido so far. And then just kind of reflecting on what happened yesterday. I'm going to skip through these slides. It seemed like a lot of the focus, honestly, yesterday was kind of on the top of this chart here in terms of people, human capacity, governance structures, engagement, and sustainability. So, you know, I'm thanks to Matt for putting this up and presenting this, but I think it's good to keep this in mind as we have our discussion. What are the components that we're talking about? So, if you want to go ahead and put a quick link to the Slido, and we'll see what we have up there, and then we'll move forward. So we have a few, you know, you can see that we have a couple of different suggestions on here for Friday topics. And please get on this Slido, upvote topics that you feel might be of interest. So that's kind of how we're proceeding as we move through these, you know, workshop days. And then we'll have a final review of this tomorrow morning to see what makes the most sense to move forward in discussion. So please add your comments and ideas and voting to the Slido. Okay, thanks. With that, I'll hand it off to Jackie.
Thanks, Doug. Good morning, everyone. We have a full day of plenaries. Our plenary session this morning is Data Commons Analytics Research and Educational User Needs. So we're going to follow the same format, as Doug said, that we did this yesterday afternoon. And so the presenters have a full 15 minutes to give their talks, and then at the end we'll have a Q&A session and discussion. So let us begin. Our first speaker is Kevin Goebbert. Welcome. Kevin, progressives. Dr. Kevin Goebbert, did I pronounce your last name correctly? Is a professor of meteorology at Valparaiso University, where he has taught undergraduate students since 2009, with a focus on synoptic meteorology and meteorological computing. Sorry, I haven't had my coffee yet. Recently, he developed an online educational resource entitled Introduction to Weather Technology using MetPy, which is designed to develop basic Pythonic computer coding skills alongside meteorological data analysis and visualization. Welcome.
Thank you.
Can I give you 5 minutes when you have 5
Sure,
minutes?
that'd be great. Great, thank you. Good morning, everybody. It's so wonderful to be with you all, to be thinking about data. They had me come up with a title weeks before I actually made the presentation. And so this is what we got: data everywhere, but not a byte to process. So my background, largely in education. Valparaiso University is a primarily undergraduate institution. We do some research, especially with our undergrads, but that is the context for some of this. As well as I've also served for about the past decade on Unidata Users Committee, which is part of the UCAR kind of grouping there. And so one of the comments that always comes up in most of those meetings is data. We got lots and lots of data. And so what I've done here is I've listed just a whole bunch of the data sources that have come up in most of my work through the various years working with students, working on my own research, those types of things. Some of the very common ones kind of in this left-hand column, model output, right? Surface data, upper air data, reanalysis data, which may be related to some of those other pieces of data, satellite radar, sea surface data, precipitation, you name it, right? You have your favorites. Those are probably on this list, or if they're not, they're definitely in your hearts. On the right-hand side here, we have other sorts of data that are maybe not as common in some of my workflows, but are definitely important elements out there, especially as we think about the movement of our science at this intersection of both weather and doing just the science, but the people, right? And one of the common things that has already come up in our conversations here are the people. So climate indices, local storm reports, convective forecasts, historic hurricane tracks, hurricane forecasts, the nebulous field study observations. That can be anything and everything. Had the privilege of visiting the airplane facility last October when I was out here, seeing the planes, lots of data coming from those as well. All these things can interact. And if we think about this lots of data, I start to get heart palpitations thinking about all the different formats that are associated with these things. And so the next slide, lots of data formats, right? So we have some of these very strong and widely utilized ones, right? NetCDF, one of the most ubiquitous data sources, especially around structured gridded data, also generated out of NSF Unidata. Our new entrants, they've just entered the chat here, if you will, ZAR format. We've got our ever lovely and everybody loves GRIB formats. METAR. Anybody still read their METARs daily to get their weather observations? Yeah, go METAR. Is that really a format? Well, okay. Buffer, NexRad. And then, of course, we've got tabular data. How many formats of that are there? Hundreds? Thousands? CSV files, another 100,000 different formats, right? Shape files, right? I know we have a few kind of geographers out in the crowd, and there's some great skills and utilization there. For any old folks in the room, GEMPAC. GEMPAC. Geotips, yeah, there you go. So, and then what about all those other undocumented binary formats that may be existing on disks somewhere, right? I mean, anybody ever run into any issues with data? No? Oh, great, we can all go home, right? It's great. Not only do we have lots of different data, which have its own peculiarities, own challenges, both in understanding what it is, their error rates related to those things, but then we have all these different formats as well. And then, of course, bringing back this image, which we saw yesterday, the volume. The volume is getting obnoxious, right? For even just thinking and finding, let alone processing, not even thinking about processing volume, just knowing what we have, utilizing what we have in meaningful ways. And again, this is just the NASA archive, right? Which is, I really didn't even put any NASA data on my first slide, right? Maybe some reanalysis, right, fits in there. Obviously field projects in ways. But we've got a massive data problem, right? Both processing, knowing where it is. Is it all good data anymore, right? Is it still stuff we can read in? I mean, some of these old data formats, maybe we can't even physically read them in anymore. The person who knew the binary is no longer doing the work, right? All these things. And so then, of course, with this data volume, we get the adage, pull, don't push, right? I'm of the generation, right? The good old days, if you will, right? Where I want all the data. Give me all the data. I'm going to pull it in. I'm going to use my LDM. I'm going to get every her time, every file, right? but not sustainable, right? I can't, one HER file, gigabytes worth of data. Well, I've maybe got 500 gigabytes to store current data. Well, that's current data. Now, what about past data, right? What if I'm looking to do, a case study back in the day? And so we want to pull only what we need. But pulling only what you need may have some challenges as well. So go to the data, right? That's been the adage. That's been the adage. How many of you have quickly adopted going to the data? Yeah. Notice only a few hands raised in the audience, right? We got many different options, right? But there are challenges with these options. Like, what's available on these different platforms? How accessible are these platforms to your workflows, to ways of getting on there? Obviously, I've utilized the big data project that got started at NOAA through AWS. They've made it relatively efficient and easy to then just pull the data down, right, instead of going to the data. Because again, these are massive changes to our workflows, right, and massive changes to how we need to operate. And so it ends up being culture change, right? Unidata, back even I think two cycles ago of funding, was really kind of getting into the cloud to understand where we need to be as a field for our researchers, for education. But we've not yet seen a large adoption because of the barriers, because of the at least perceived barriers to going to the data in efficient, effective ways, both cost, time, and personnel. And then where are the data I need? Right? Again, I'm a synoptician, so I'm largely looking at data. And there are some absolutely fundamental data sources here that I would be up a creek without a paddle. If Daryl Hertzman was not storing data like a good hoarder he is, I'd be in a world of hurt, right? And my educational process would be in a world of hurt. Wyoming, with their sounding archive, in a world of hurt. I mean, because it's accessible. It is relatively easy to get. But if I want old satellite data, I need to go order that and wait for it to process and come back to me. Not super accessible class archive out there. Other good climate data available from the Applied Climate Information System, right? Obviously, we saw NASA has all of its data. We've got our various NOAA centers all over the place, all serving data in various formats in various ways that are variously accessible or not. We've got Unidata serving some really great real-time data for us. We've got the RDA that's got a plethora of stuff, again, available in different ways. And then we've got, of course, the buckets out there, right? And so I've got AWS buckets out there. But am I in the East? Am I in the West? What's in the East? What's in the West? Am I not even from the US? So now I'm not even in that bucket naturally or stuff. And what's there? I don't know. How do I keep up with it? Then how do I access it? Right? If I got CSV files versus NetCDF files versus GRIB files versus is it on a cloud? Is it not on the cloud? Is it georeference? Is it not georeference? Is it radar? We've got some wonderful tools out there. But they're so varied because our data sets and our formats are so varied. How do we keep this all in mind, right? And so the question that I was ultimately asked, right, was what are the needs, right? So I'm kind of the big build up here, right, to this idea of what are the needs of our community. So not a byte to process, right? This has really come back to bite me in the past year or so, right? The idea that even if I know where my data is, so I've overcome that challenge, even if I know maybe the best resource for reading and processing that data, there are still lots of problems with our data in order to actually do it well. And so when you're trying to teach a new student who is theoretically a digital native but has never really done computing, right? They've tapped things, right? Everything installs beautifully, right? They don't have 6 disks to put in sequence. They don't have to have separate boot up things in order to get your SimCity 2000 running on your really old computer, right? That really, reading this data is but the tip of the iceberg, right? At the end of what can be a very, very long journey, right? All the way at the bottom is just getting the data, right? Which is that findability piece. But then what if there's not metadata? Or the only metadata is in the file name, like the time or the location. And then non-compliant columns or columns that have both strings and numbers. Now our data formats are not being read in really well. Time. Time. 24 hours, 365, sometimes 366 days in a year, right? All these things are all challenges that we face. And then that's not even getting into Have the data been QC'd? How do I know if they've been QC'd? How well have they been QC'd? Do they just flag the data? Do they remove data? Lots of things going on there. And then failures, access failures. This is the one that has really kicked me because of either data limits, although that's generally not been too big of a problem for me. URL changes. Those have been the real kickers of all of a sudden like, oh, hey, this workflow that worked 2 weeks ago. Now I go and nope, not there, not there. Sometimes data sources, we're storing data for a while, and then all of a sudden, no, we're not, right? NAR, for example, right? The North American Regional Root Analysis was being stored for a while in one resource, but is only available through 2014, even though new data continues to generate. Why? You know. Probably data storage limits, right? These limits that we have on our data. Or files are moved to historic units, right? We have this weird conundrum, right? Our data aren't just in the past. They are in both the present and the past. Right? We have operational needs, right? We want real-time data. We want to be able to do forecasts. We want to understand what's going on right now. We want radar from today, right? Storm's coming. We want to see it. But we also want to be able to go back 5 years from now and go, hey, I want to find storms that are all similar and put those together in a way and study them. And so sometimes we have them in live units, and then we have them in historic units. And when they transfer over is not exactly communicated. Then all of a sudden this workflow like, oh, yes, I'm able to access data here. And now I'm not. I need to build if statements in to then be able to access my data properly. Or things change and an access method that I used before, maybe it was OpenDAT, maybe it was a NetCDF subset service is no longer being supported on whatever the new system is, or there's a newfangled thing that I don't even know about yet, and now that's how it's being offered. And so this access denied, right? These barriers to then successful use of data. And I think that's the biggest barrier overall that we face in this idea of thinking about a data commons is how do we create the on-ramps, we talked a little bit about this yesterday, that have a high chance of success because for each failure, you need 7 times of it going well in order for something to be adopted. And when you're working with new students or when you're working with folks who have older workflows and getting them transferred over, that can be a real barrier. And I think that's been one of the main reasons we've had challenges in getting our moving to the cloud, right? Moving to the data in so many different ways. So what are some of these overall research and education challenges from my vantage point here? Ever-changing locations of data, right? New data come online. Where is it now? Where is it going to be? Is it stored in just a format that, yep, it's there and available, not really curated, all those sorts of things. That our data continue to evolve, right? GFS has been around now for a good long time. Was 2.5 degrees, or 1.5, 1, half, quarter now, right? And all those have different time spans. And it's good that we're getting higher resolution, but that presents challenges for us in being able to communicate and use that data well. And so ultimately, our data workflows are actually very brittle, right? What I should have put in here was the good XKCD comic, right? That has the like block tower that has this one package that's like literally holding up the entire domain, and that if that goes away, boom, it's going to crumble to the ground, right? Our workflows are really that brittle, right? They are reliant on some good graces of people or some funding from things like NSF that may not always be there, that all of a sudden could really break our workflows quite quickly, as we've seen just from changing a URL, and that there's not the ability to easily, gracefully move through that. We have very brittle legacy data formats, right? There is a wealth of data, again, due to Daryl Hertzman, of GEMPAK archive data. I used that for many years when I used GEMPAK as the primary teaching tool to do synoptic-related stuff. We've now ported some of that ability to read that data into MetPy so that we can read it. But again, maintaining that long term is going to be a challenge. And now we've got this great archive that may or may not be able to be used. And these brittle legacy formats, or formats that aren't appropriate for long-term storage. Get to that in a second. And then just our general need to convert formats for modern science problems, i.e. AI/ML, right? Our data aren't often stored in a format that is generally preset and ready to go for that. And so how do we do that, and how do we store that separately? Do we not? Those are some questions that would need to be addressed by each individual community as we're looking to do things. So what we need, curated, CF compliant, archive data. Note I say archive data here. Distinction between transmission formats, GRIB, and storage formats, not GRIB. Less brittle infrastructure overall, and that really this idea of medium data solutions. This is where I find myself most often. The small data solutions, yeah, you can download your data, boom, do your work, great. Big data, yeah, go to the data. That might be the most appropriate thing. But this medium data, where I need like maybe gigabytes worth of data, but I don't really want to download it, but going to it is a larger barrier, what's that doing? So ultimately, we want it so that we can all get data as Oprah tells us to. So that's it, and I'll leave it at that. We'll have obviously questions and questions in the form of a comment at the end. Thank you.
Thanks, Kevin. And we will have opportunities for questions in the end. Our next speaker is MaKenna Collins. Sorry about that. MaKenna, did I pronounce your name correctly? MaKenna Collins. MaKenna is a rising senior at Jackson State University, scheduled for graduation in spring of 2025, with a focus on Earth system science and a minor in sociology. Engaged in diverse projects from creating a Jupyter notebook for retrieving NOAA tide gauge data to studying severe weather and climate impacts in the southeast region of the US and analyzing a rock core from the KT boundary. And I'm going to let her introduce your presentation. I'm going to give you 5 minutes.
Yes. All right, good morning, everyone. Thank you so much for that introduction, and thanks to NCAR for inviting me and giving me the opportunity to come speak about some user needs. So today I'm speaking on the subject of finding the common denominator. And I just want to provide a brief background just to give more context of where I'm coming from in this presentation. So Earth system science is definitely very interdisciplinary, and majority of my data work is during summer internships. So just to say, I don't use it all the time. So just give, kind of not put myself, but maybe I end up on one end of the spectrum versus, plenty of scientists in this room who may be on the other side. So just a little context about me. Okay, so I know I'm talking about common denominators, but y'all, this is not a math lesson. Don't worry, it's gonna be informative, not scary. So yeah, let's use the idea of the common denominator in our data commons. So, of course we learn in school that pretty much for fractions, you want to perform your basic tasks, adding and subtracting, you need a common denominator. And I think if we apply the same commonness to our common denominator, put more people on an even playing field, we can tackle more things with more diverse communities. Okay, just to recap and restate what NCAR said, I really enjoyed this sentence, so just wanted to share it again. The purpose of a geoscience data commons would be to allow a broad and diverse user community to share, integrate, analyze, and visualize geoscience research data to drive scientific discovery. So beautifully said, I couldn't have said it any better, and honestly kind of put more into focus why we're here and the purpose or I guess goal of a data commons. So just two things just to emphasize, it's the broad and diverse user community. We're targeting more people than scientists. That's kind of the accessibility route that I'm gonna try to talk about today. And then the 4 actions: sharing, integrating, analyzing, and visualizing. 4 key components of the research process. And I appreciate how it's worded here, and the broad and diverse user community needs to be the ones who are performing these actions. So whatever comes up in the data commons needs to be applicable to a variety of users. Okay, so like I said, I don't use data every day, all these things. So I had to do a little research, and I came across this information on data.gov. And I won't spend too much time on this because, I learned about FAIR yesterday. And I know we all know about the FAIR, accessible, all those type of things. But just to emphasize and highlight 2 of the things that kind of geared my ideas for this is 1, the accessible section, and 2, describe. So for accessible, I really appreciated how they worded this. They say, open data structures do not discriminate. And I really appreciate the use of the word discriminate here. I think it adds power and, just power and emphasis on why this data needs to be accessible. Discrimination is a strong term historically, and using it in this context kind of call to action in a way. Describe, whoever wants the data needs to know all they need to know about the data, its limitations, their limitations, security requirements, all things like that. Okay, data commons. I first started thinking about common things. So in my high school, we had the center of our school called the Commons. We had lunch, banquets, dances, whatever happened in high school most likely happened in our commons. So when I'm thinking about a data commons, I kind of think of other common spaces. And yeah, I want y'all to think about some common spaces. What are common spaces, common things, common ideas that people share? So yeah, and think about characteristics of those common things. In the case of the commons, or in high school, it was a huge room, multifunctional, and that's kind of a characteristic we can apply to our data commons. It needs to be big, it needs to be able to hold as much data as the users want and need, and it also needs to be functional and things like multifunctional, let's say that. So when I was thinking about other common spaces, I was thinking about airports, they're big, multifunctional, the mall, get some food, some shoes, whatever you want. So just common things. All right, and just to add to the definitions of data commons, this is like a combination of other definitions and the NCAR purpose statement. A data commons is a managed collection of data, resources, and other tools accessible to users to support the sharing, integration, analysis, and visualization of geoscience data. Cool, just adding it to the pot. So yeah, we know all about the goals, but just to emphasize a couple here, I'm gonna emphasize accessibility because I think that's what we're trying to reach here during this workshop. We want more people, broad and diverse user communities, of course, to come in and access the data with no problem. So, of course, accessibility, collaboration, when we even out the playing field a little bit with our data commons, we can support that interdisciplinary research, whether it be between labs, between disciplines, earth science versus meteorology, whatever have you, coming together to make better products. And sustainability, of course, we want to make sure the data commons and the data itself is valuable and is just there for not only this year that it was produced, but for the next 5 years, 10 years, so have you. Okay, so when I first, got this invitation to this or workshop or presentation, whatever, I was a little nervous because, like I said, I don't use data every day. But my friend / peer mentor, she kind of reminded me that I've worked with data before, so I know a little bit. So I just want to share a few examples of some data commons or data sources, whatever you want to call it right now, that I've used and some things I liked and maybe some improvements to those. And maybe that can be applied to kind of what we see in our data or our new data commons. Okay, so the first time I ever tried to do research, data, things like that, it was a summer going into my sophomore year. I was doing a climate variability project, and I was working at the National Weather Service in Jackson, very small office. I don't know, maybe y'all have experience with National Weather Service data, but in my opinion, it's not that accessible. It took a lot of steps to get from this website to, at the time I was using RStudio. So, and mind you, of course, that may vary based on your experience, but for me, we're trying to increase accessibility, broad user community. As a, a broad user, it was challenging, y'all. So this is what it looked like. As you can see, it's like, I don't know even how to explain it, but yeah, just the fact that it took a lot of steps to get from there to the commons. But something I appreciated about the website was this frequently asked questions. It provided definitions, kind of like a glossary in a sense of meanings of the data, and I think this was really helpful, especially for us who didn't produce the data, so we don't know what these things mean. I will say I wish this was included more in the description, not on the frequently asked questions, because that was a smaller section, but I appreciated that it was at least available. Okay, so this is what I worked on last summer. Well, I didn't work on this, but this is what I used last summer. It is the Co-ops API URL builder. This is honestly the most accessible data source that I have used so far. Basically, it's a website. Put in your station ID, your parameters, things like that, and it gives you the URL, copy and paste into your code. You're cool. So my project about this was I created a Jupyter notebook detailing this process. You can download it right now on the Co-op's GitHub if you want. But yeah, you can do whatever parameters you need. I appreciated the organization of this site, how it has the data, metadata, and derived product API, so you can work with primary data or aggregate data if you want. And one thing I will say, mind you, it's a great product, the best one I've used so far, but it's kind of limited. So the data comes from the tide gauges, and there is over 200 of them across the United States, but they're only at tide gauges, What about the real like National Weather Service centers, things like that? So yeah, I just wish this data or this process could be used for other centers, things like that. All right, and for this example, I hadn't done a full project on it, but I just wanted to see the process of like accessing the data. And this is where I came, and if this is not like where I'm supposed to be, that tells another story. But this is what I came to. Here, I really appreciate it. It tells you how many sets are available, the sorting, I like that. And over here, downloading Python script, it brought me straight to my environment. So that was cool as far as accessibility. One thing I want to see more, some descriptions, and I'll talk a little bit about that later. Okay, so we know all about the 5 W's, who, what, when, where, why. Okay, what about the how? So, some sample questions here that address those 5 W's. But honestly, as a user, a beginner user, the how was majority of the questions that I had. How do I download the data? How do I get to the data? How do I do things with the data, And I understand that a data commons is not necessarily the space for a classroom. It's not a classroom. So it's not a place for necessarily to learn. But when we're talking about different data sets and different producers of those data sets, I do think some type of direction on how to work with that specific data set would, kind of help users out. So focusing on the how in these user needs. So, 5 minutes, good. User needs, some that I came up with, more thorough descriptions. Like in the National Weather Service example, those were good things to be included in the description, not having to search too hard to find them. In the description, we want to see kind of like a glossary in a way, how the data was collected, why, what could the data be used for, just things like that, so people who want the data know exactly, like I said, its limitations, their limitations, things like that. Brief instructions to address the how. And emphasis on brief here, because like I said, a data commons is not a classroom. It's not somewhere where beginners should learn, because there is Stack Overflow, Geeks for Geeks, all those type of things. So it's not that place. But like I said, since our data and the producers of the data don't really do it universally, having those specific instructions that just apply to that data set, those abbreviations, things like that, to let the users know how, what this does, things like that. All right, show what can be done with the data. Oh gosh. When on the co-op's site, when you press URL or go to URL, thousands, hundreds of thousands of numbers, crazy to look at. So it's a little intimidating. Beginner users, a little intimidating to see all those numbers. So maybe providing already done product to give users an idea of what can be done with the data. All right, user-friendly access. Again, with the co-ops, very user-friendly, straightforward, brought you straight exactly where you need to go. Resources and support, and this one is not to get overcrowded in the data commons. We need most of the space to be for the data, for all the type of discoveries that need to be happening. But resources as far as, I don't even want to say manual, but just any type of support. I know in our breakout session, we were talking about the point of contact, or how they get so many emails. And it's not even necessarily an email. There was a presentation, I believe Deepak talked about giving the users the tools to figure it out themselves. And honestly, as a beginner user, I think this is a good idea to encourage our own scientific discovery and add to the scientific discovery that's already happening, giving us the tools and the things we need just to read, maybe a video to watch, things like that. Options, we want to see different formats. We want to see data from different offices, different centers, things like that, and regular enhancements and additions. So upgrades, making sure the URLs are good and things like that. Timely data, we want to study a storm that happened last night, maybe, and we should be able to do that, So, yeah. Now, as we go out into our breakout sessions, I want to encourage us to make our denominator common. So I have a denominator, you have a denominator, you have a denominator. Everybody has a denominator. And I noticed that when we were doing the key ideas, big ideas, after we did our breakout sessions, a lot of those ideas overlapped. And those are the denominator. Those are the common denominators that we can, or those are the, let's say, multiples and factors that we can apply to find our denominator. So encouraging us, imploring us to keep it simple. I know a whole lot of scientists in here. aspire to be like y'all. But when we're talking about diverse user communities, not everybody looks like and has the education background that y'all have. So just encouraging us to keep it simple, level out the playing field, and yeah, that's it.
Thanks, MaKenna. Good luck with your studies. Our next speaker is David John Gagne. David is a machine learning scientist and head of the Machine Integration and Learning of Earth Systems group at NCAR. His research focuses on developing machine learning systems to improve the prediction and understanding of high-impact weather and to enhance weather and climate models. John, I'll give you 5 minutes. Okay.
All right. Thank you for the invitation to speak here. Today I'm going to talk about machine learning data challenges across the whole pipeline. So the kind of motivation for this is that because of all the attention things like ChatGPT, as well as all these new AI weather prediction products, as well as the whole large amount of AI systems that have been built up in the past decade or so, have all been moving from kind of these proof of concept, bespoke, sort of standalone systems to things that are being more commonly deployed by a wide variety of users and not just people who are AI experts. The whole space of how AI systems are being used is changing quite rapidly. But the readiness of both the AI systems, the software, and the data pipelines for all this varies wildly. There's still a lot that is being kind of built from scratch or on the fly or trying to piece together a lot of existing tools. And one of the issues with this, especially from the data side, is that as this one paper called Everyone Wants to Do the Model Work, Not the Data Work points out, a lot of the issues, basically, if you look at the diagram, basically when you actually deploy these systems in the physical world and in different domains from which the clean, nice data was trained in the real world data, much messier, you get what are called data cascades, where basically your failures prop up that cause you to have to basically go back to the very beginning and start over again. And that's a very expensive process, especially when we're starting to use these bigger and bigger models and on larger and larger data sets. What are some? I wanted to go through kind of the whole machine learning pipeline and kind of point out some areas where there are issues and where there are potential ways to, some tools that we're working on here. Also, some other maybe hey, this is coming, giant train coming your way. Maybe that there's some ways to put the brakes on it before it smashes into everyone. So to give you a sense of how AI is starting to be used across NCAR. My group, the Miles group, we're kind of in the middle of a bunch of different projects spanning across not only different labs, but also government organizations like NOAA and NSF. We're also working with large projects involving university collaborators and private sector and government agencies, including things like AI2ES and LEAP and M-Squared Lines and Catalyst, as well as working with people like Unidata and the broader education community, the universities bringing in visitors and running short courses in summer schools. So we're engaged with AI across a wide range of data sets and problems, and kind of work with a lot of different users. So we see both the possibilities, but also all the challenges and messiness that goes into this process. Starting on the data preparation side, this is where most research, data scientists and machine learning scientists, most of them spend most of their time on getting the data into the model. And there's a lot of challenges that come into this. I mean, one, if you're familiar with any kind of data analysis problem, trying to build a machine learning model makes that harder, because not only are you just pulling data for a case study, you want multiple years of data from different events and a good sampling to have a robust model. So then you have to think about what scales are relevant. Do I need the super high res data? Do I care about things going across scales? Because that's the exciting science question. So maybe I need global data. Do I need gridded data? This is a thing I care about more like a blob. Do I want to analyze it as a blob? How do I go from grids to blobs and back to grids? What variables do I need? I discovered I need more variables because I did this whole pipeline, and now I'm missing some key physical feature. How do I go back and grab that? then often sometimes the things we care about predicting are things that aren't nicely cataloged in the data, aren't like a numerical value. Sometimes we want to say classify storm mode, or how did someone react to a weather event, or where is this phenomenon that's kind of subjectively defined in some sort. So sometimes you can use an automatic label, but often you'll need some kind of manual label, at least also to QC your process. Manual labeling has its own set of problems, including consistency and confidence in the labels, which you could record as metadata, but maybe a lot of people do not. There are methods in different communities to measure even the reliability and how to train people to label data, but the awareness of those is fairly limited. There's also how long are those data labels good for? Do they, if you change something in your data pipeline, suddenly the label isn't valid anymore, and maybe you have to go back to relabel it. How did you get those labels? Were they done by experts, or did you go on Amazon Mechanical Turk, and was ChatGPT actually labeling it behind the scenes? Making sure people, when we deploy these models with users, one of the things they care about is how is this being processed and labeled. So having good data provenance, not only on the input data, but also on other data you're bringing in, is really important. Another topic that's come up a lot is AI-ready data. A lot of funding is, we need to make our data AI-ready. What does that mean? No, I think there's been multiple workshops, so the conclusion is we don't really know. And I think one of the problems is that a lot of steps in making data AI-ready are things that don't generalize well. So there's a lot of the data transformations we have to do to get data from its original data sources into something that is ready for ML model are lossy. So most of the things are on the left. I mean, it's reshaping the data, rechunking, maybe changing the format, although you have to keep the same precision and stuff, so that even that's not completely lossless. And maybe you can do some lossless compression, but then if you want to regrid, that introduces errors. Subsampling, now you're throwing out data. Rescaling, the kind of normalization you have to do in every single machine learning model for any kind of neural network or regression, that is a lossy compression. You do not, if you try to go take the same data, go forward and back, even if it's just subtracting the mean and dividing by the standard deviation, you will not get the same values back. It's a lossy process. Imputation, there's always going to be some kind of missing data, even in model output sometimes. So how you do that is a decision that affects the data. Matching data sets from separate sources. We saw in Dr. Yobo's talk yesterday examples of how you match a nearby observation to a particular location has a big impact on, if you don't understand the physics going on behind it, or the demographics or the other context of that problem, you can give some very wrong results when you do that, and it imposes incorrect information. Feature selection as well, what do you choose to bring in? So how can we get past some of this? Is there a way? I think in some cases there may be some ways, and some of the things that have been discussed might help. Moving some of the data processing into the model step may also help with some of these things and make it easier to pull, so you don't have to make as many copies of the data. But I think for most problems, there's still going to be some copying involved and some transformations that we're just not going to be able to avoid. But maybe we can, if we have storage size constraints, maybe there's some other ways to help with that. I'll talk about a couple of those in the next couple of slides. As we're also processing the data, we also need to be aware of all the biases that can happen in the AI pipeline. I'm a co-author on a couple of papers that discuss this in a lot more detail. But this includes issues with both your training data and the biases involved with that, issues with the AI model itself and how you train it, and what kind of model you use and how you evaluate it. And then just kind of the politics and kind of societal constructs behind deploying AI systems in different areas, and kind of the user, as well as broader implications for if a group is using AI models instead of a more traditional method, how does that change the game? There's still a lot of open questions there. There's also biases that creep in at various points that we can't all get rid of, but maybe we can acknowledge and have some ways to make the users more empowered to basically be aware of them and find ways to counteract them. There's also getting AI into our numerical models is an increasingly big challenge. We're working on that at NCAR and thinking through some different ways to do that, but each of them have various trade-offs that are involved with that. And then now you have to have a process where you're interlinking Python and Fortran, and it's still, like, even for experts, it's still really hard. So we need to make this is a big bottleneck, and doing kind of more combined analysis, or preventing us having to, like, save out a ton of model output that we then, like, interrogate online. If we can do everything online, we may be able to save out less data and relieve some of our storage costs. One way we can potentially get around some of the issues of these, like, lossy data issues is being able to use distributed pre-processing techniques. So one I've been working on is called Bridge Scaler. Part of the idea of this is to make it easier to save out the scaling part. So when you normalize your data, you want to be able to save out the data in a way that, like, when you upgrade your version of scikit-learn, it doesn't automatically break everything. So you can still recover the important information out of that file if needed. I've also been working a lot on distributed scalars, so that if you either have a big parallel supercomputer, you can process a giant amount of data really fast, or if you only have a limited amount of compute, you can stream in a little bit of data at a time, calculate your normalization values as you go, and then you can bring things together, take things apart as needed. When we get to the actual ML model training part of the process, like, there's still a lot of work to be done on figuring out what needs to actually be saved to be able to reproduce the machine learning modeling pipeline. So there's an increasing number of packages that help with this. So one is ML Flow, that's fairly open source. I show an example of this. In addition to saving the model weights or the model object itself, you need to save the scalar. There's other metadata about, like, what Python environment, what version of TensorFlow did you use, and all the other dependencies, because sometimes minor changes in any of those will break that whole pipeline, which is still a problem, and it's still really frustrating. Maybe you want to track how your, like, various metrics you're using to train the model are changing, as well as maybe, like, how well are you utilizing your GPU, or how fast are you bringing in data. Like, all those are important to debug your process so you can speed that up. And this creates a lot of data by itself. How do we store that? It's still a very, like, fluid area that there's not really any standards on yet. But more people are training a lot more models, and, like, some people are doing tons and tons of experiments that require a lot of GPU hours. And if we want to utilize that to the best use possible and not produce a giant carbon footprint just from, like, doing hyperparameter searches, we need to think through how to organize this data more effectively and make it more accessible to different users. Other thing we're working on that's kind of coming down the pipeline is we're making it a lot easier to train AI NWP models. We're in the process of building and releasing a new AI NWP package called Credit. We're aiming it to be a community model for AI numerical weather prediction. This is an example of one of our more recent runs. We've got a lot of high resolution features. We're producing hourly global output at 1/4 degree resolution. And once trained on, like, 32 GPUs for a couple weeks, we can run it in, like, seconds on one GPU. Of course, if you're data people, you should probably be, like, quaking in your boots when you hear, oh, we can produce hourly 1/4 degree global data in seconds, because lots of users are probably going to start doing that with their own models, and now you've got this giant avalanche of numerical model output being created. And what are we going to do with that? How are we going to this problem is only going to get worse as we kind of, like, have these step changes in what new kinds of compute systems can do and how fast they can push things through. So new bottlenecks are going to be created, and how, like, I think it's a question of how to deal with that. We're also don't just care about weather data for the sake of weather data. We want to interact with people data. So this is another merging of different data sets. We used basically machine learning models from convectional output to predict tornado probabilities, tornado counts, as well as generating 10,000 tornado tracks per, like, 20-kilometer grid cell per hour. And this for one case. We generated, like, 1 billion synthetic tornado tracks for this one case, and intersected this with 100-meter hourly population data. So that's a lot of data to process and compute and track. And now we're also bringing in different organizations and their data assumptions. So it's and this is just with population, not getting into vulnerability and all the other, like, things that one could do with this kind of stuff. So again, another, like, what do we do with all this data that the ML models are enabling us to produce? Open question. So to kind of end, I think basically the work that this put the AI ready, cloud optimized kind of banner on here, but like, what does that actually mean? I think having more reforecasts and model archives and supporting that in some way that is somewhat sustainable, like will enable a lot more AI training, but then that produces more data. So how do we deal with that? I don't know. I think making our observations more accessible. There's a lot of small data that's really key for training models well, and making sure that is well processed will enable a lot of, I think, small data machine learning that isn't so compute heavy, but is key to making all this stuff better. I think we need better interactive visualization and make it easier for people to do interactive visualization so they can look at their data. That's the way to find most of the problems. And working with social scientists and the broad community of users, and including people at MSIs, to understand their needs and impacts, and like tailoring problems to their local communities, so that we can address the common denominator, as the last speaker mentioned, the common denominator users. So I'll leave it there and happy to take questions at the end.
Thanks, David. Our next speaker is John Vandergriff. Did I pronounce your name correct? John Vandergriff. John is principal professional staff at the Johns Hopkins Applied Physics Lab. He supervises a group of 50 RSEs, scientists and engineers who create tools and perform analysis on space mission data covering mainly heliophysics and planetary science. He coordinates the development of the Heliophysics Application Programmers Interface, a grassroots community effort standardizing accessing to time series data.
Need the mic up here?
Yeah.
Okay, should have been doing that.
Is it on? Yeah.
Okay, all right. Thank you. All right, yeah, great to see everybody here. This is an awesome meeting so far. Thank you for the chance to talk about this. So my original title is The Small One Role of APIs in Distributing and Sharing Data, the HAPI example. I've kind of tried to broaden the topic to, it's moving automatically, to data analysis in geospace, and I'm mostly talking about the heliophysics part of geospace. And the HAPI project involves myself and a lot of other people. Bob Weigel from George Mason has been involved since the beginning. So the heliophysics, well, here's the outline, some analysis examples, and a key point, what I'm calling the fill my array problem, and how APIs can help with that, and an example of one API that's working. And then if I have time, we talked a lot about cloud capabilities, and we're also working on something in that regime. So a lot of people have mentioned this. Data is coming from everywhere. And in heliophysics, this problem is illustrated on the left panel here. You have all these different missions measuring many different types of phenomena of all different kinds. Images of the sun, movies of coronal mass ejections, in situ measurements of plasma and particles and magnetic fields. And then on the kind of the space weather side, the picture on the right, the words are too small to read. It's just, you can kind of see the domain there. And of course, none of these pictures are to scale. We make these crazy cartoons, but the concept of the communications issues that arise from solar radio emissions and the atmospheric puffing from energetic particles causing satellite drag, and there's even currents flowing in the ground that can affect pipeline corrosion and power line transmission issues. If we had a really big coronal mass ejection, it could actually burn out transformers. So there's a lot of operational considerations. So the main point here is our data comes from everywhere. And so here's an example plot from one paper. I'm not going to go in detail over what all these different panels are, but I just want to emphasize that to do this analysis, it required data from a lot of different places. One of them is ham radio data. People are voluntarily making available their connections. Can I talk to this station there? And where do we think the midpoint of that ionospheric bounce was? Or radar backscatter data, or GPS data about that you can get total electron content of the ionosphere. So you need to combine all of these, and they come up with this really interesting result that there's disturbances travel through the ionosphere, and you can see that in these time series. So The point here being, any paper doing analysis has to be combining data from a lot of these different places. And we saw that slide of, well, a lot of the effort is getting that data in there. So for scientists, where the rubber meets the road is what I'm calling the fill my array problem. Because scientists, they don't really care about all these data systems and formats. They just want things to show up in their code in a usable way. And so they'll write this read data routine. It goes to grab the data set they want based on their criteria. And then it shows up in some structure that they know and love. I've got my mag data. And now that's what they run with. They can feed that to other things. So they don't really care how that happens. But then they can use that from all the different sources and do whatever they want with it. So pictorially, the data comes in. You have to write data wrangling code. Then it gets into the structure that you want. That's like the mag data thing I was talking about. Then you do your analysis with it. But of course, there's other data. You need to write more data wranglers. You get other things. You end up writing a lot of this data wrangling code. So this is what we've been talking about. So a lot of different data centers. These are all different heliophysics data centers. I'm not going to explain the acronyms, but they're all different, independent, completely independently funded. Some of them are NASA, some are NSF, some are European. And they all have their own API where you have to write the data wrangling code to get to the analysis. And so they've all done their due diligence. They provide a web page describing, hey, here's how you access our data. And so the first one, C2Web, they have their description. Madrigal has theirs. And that one's been around for a long time. Katherine's here. She can answer questions about that one. Intermagnet has their description. The Swarm mission has a whole analysis mechanism, and it keeps going. There's a Space Weather Data Portal at LASP. There's a University of Iowa data server. There's another European server. They all have their web pages, so you have to read all these web pages. And so what we've done in heliophysics is we recognize that these custom APIs were not that different. They all had some common elements. So we created what we call the Heliophysics Application Programmers Interface that identified what we talked about, the lowest common denominator. Here's a way to access this tabular data using one API. And these different data centers, they don't tear down anything. They leave their custom API there, but they add this additional one. And now you can get to all of these different data sources with a single piece of code. And piping it through that one mechanism, I mean, that's the benefit of a standard. This isn't rocket science, but it's that social engineering. It's 5 years of social engineering to get people to agree to do this. And so, because everybody had to give up something to get to the lowest common denominator. And so, but once you have this single access point, I didn't list all the benefits, so I'll mention some others, but basic, simple discovery. We didn't really focus on the discovery part. The metadata is elsewhere. You can find this data, but this is, you get simple discovery, like the API involves a way to say, well, what data sets do you have? And you get a list back. So you get a unified, simple discovery, but the main point is standardized access, the fill my array problem. Get me that data into my software. And once you have that, this is an API. This is language independent. So there are implementations in Python and MATLAB, even IDL. We have one for Java. Someone contributed one for R. So you know, it's a language independent way of accessing things. And it can serve as a foundation for a whole bunch of other stuff. You want to fuse data. You want to visualize data. You want to come up with some data cleaning or a visualization mechanism. You can do it all through a single API. So we're pretty excited about this, and it's catching on. So here are some of the institutions that have adopted it. Again, I'm not going to go through all the acronyms. It's just supposed to be a long and impressive list to make you say, wow. But there's NASA. That's where we started. That's where our funding came from. AMDA is a European data center. LASP has adopted it for some of their solar irradiance data. And then the Royal Netherlands Meteorological Institute, they actually built theirs using our API, and they've developed some very useful clients. So other people are developing clients. We didn't pay for that. They're just making really nice clients. And some of the European heliophysics missions. Other institutions are on the way, still working on it. Some other European missions, some NASA planetary data. It's the same kind of data. It's time series. The Canadians are working on a Space Environment Canada project, and they want to use it. And NOAA SWPC, the Space Weather Prediction Center, is actively working on one right now. So just to prove the point, this was one application that loaded all these panels from servers all over the world. You just select it. Oh, I want this. Oh, I want to see that. And it just pulls them in all at once. So it is working. Okay. So this is kind of my main point. A standard access API, it's a foundation. And you can build all kinds of things on top of it. And all the benefits that we talked about. And so this was kind of the core piece of that, what do we do for a data commons thing is interoperability and standards. And so finding the right way to standardize what can everybody commit to. Our data could go through this, and it could survive and be useful on the other side. That's the hard part, is getting to that API. So do I have a few minutes left? Oh, okay. So I have 2 slides on a totally different thing, which is another cloud-based project. We were admonished yesterday to be careful how we use the word cloud because it can mean a lot of things. It's even worse than that, really, because we showed diagrams connecting stuff, and those lines, it's just a line, but that line means who knows what. People could use this. This is an entire ICD, or these are related. But anyway, I'm going to show you diagrams with lines related to cloud, so buyer beware. But what we're doing is we're creating a project that's kind of infrastructure as code. We're creating a set of scripts. You run these scripts, and it will instantiate. It will pop up on Amazon, so we've committed to this platform. But it will pop up a cloud-based environment that an institution or a project could use to enable cloud-based analysis for researchers at that institution or project. And the on-ramp is critical. The scientists who use this should not even know or care that it's cloud. The people building it take care of that part. So the tools that are there are familiar. This is very similar to the cryo cloud kind of experience. And there are some compatibilities between it. And we're, of course, aware of that and trying to stay in touch. So there are some differences I'll talk about in the next slide. But yeah, you could set this up at a smaller institution or just a modeling project. You can give, because it lives outside of your institution, you can give people accounts on this and let them collaborate with you. So the way it works, this is the people who are on this project would not like this slide, but I'm going to show it to you anyway just because it's very, very broad overview. So we're creating set-up infrastructure, scripts that you run, and different institutions will take that and create their own instance of HelioCloud and expose their own public data, shown in blue. And then that data becomes accessible. We have ways to have a common registry across all of the instances so that you can find data. You can have private data if you're not ready to release it yet, or you just want to work internally on a team. And then, we have a common registry mechanism that will expose this data to different users. So the cloud users, this is way too simple to explain it. The users can be specific to each one. They can access things from each of the other ones. But the point is that you bring the benefits of the cloud, the scalable compute, the managing of large data, but it doesn't require cloud expertise. So this has been, it's in use at 3 different institutions. NASA is where it started. We have our own instance at the Applied Physics Lab. LASP is using it a little bit. They spun one up last week for a Python and Heliophysics summer school, similar to the Hack Week concept that Tasha was talking about. And at the end of the summer school, all the students are saying, can you just leave this up? This is so useful. But the model that we have is that each institution will stand this up and then pay for it out of their own compute infrastructure, that it becomes a useful thing like the servers and the data stores that they already provide. We're trying to get it down into the like 10,000 per year kind of range to leave this up and running, and then people can just use it and you can share it with other users. So we think that's a very exciting option for the future. So here's my conclusion slide. I mentioned briefly about the cloud mechanism, and then with data being so distributed, the way to help with this, and we saw all the different formats that everyone was talking about, hide all of that stuff behind the right API, right? Solve that problem once and let people access it through a common API. Maybe not just the API, right? There's going to be different communities that have a different view of the data. So what is the my takeaway from this, and I think the thing we can talk about is, what's the right number of APIs for accessing a data commons? And we have one that works well for time series data. It's called the Heliophysics API, but it's not really Heliophysics specific, and so it's possibly useful in other domains. So yeah, I think that's what we can talk about as a community, is how do we come up with the right place of creating that sameness where we don't have to deal with the heterogeneity. We can start talking about the science. Yeah. Thank you.
To me, a cloud are those white puffy things outside. So, our final speaker of today is Denise Ramsawak, who also goes. Thanks, Dean. Stick around. So now it's time for our Q&A. So could I have the speakers come to the front of the stage, please? There's seats if you want, or you can stand. It's entirely up to you. We have 2 microphones, one to ask questions. You will be the keeper of the microphone, and one to respond. So does anybody in the room have questions or comments? Above microphone? Fletcher, are we using the above microphone, or should they use the? They should use the microphone. Okay.
Thanks. 2 comments and a question. First comment is on Dean. I like you mentioned Google Earth Engine because I think it's a really good example of a platform that has changed how people do science, right? Especially for land use, land cover community. They pretty much use it to do large-scale processing. The other comment is to DJ. Enjoyed your talk a lot. I think this notion of AI-ready data, I think I agree with you. We don't know what their definition is, but I think it is important for us to put out AI-ready data where the pre-processing is done by the scientist rather than the computer scientist, right? I think for us, a lot of the innovations in AI are happening on the computer science domain. And if we make our data available for them to utilize, we benefit from those innovations, right? I think that at least that's how we perceive trying to build it. The question to you is, could you talk a little bit more about the credit slide that you have? I couldn't really grasp the details of it. Is it an evaluation tool, or do you actually have an underlying model that you are using?
Yeah, so if you're familiar with the GraphCast and ForecastNet, some of the other AI NWP models, this is my group's effort to make our own system that will allow users to train and run and evaluate these kinds of models. So we're building our own and that basically our own models in this framework, and we've been starting to evaluate and run them ourselves. Some of the differences between what we're doing with the first generation of AI numerical models have been doing is we're using Era 5 model level output instead of the pressure level output, which basically captures terrain variations near the surface and then it relaxes the pressure levels up high. We also have hourly output instead of 6-hourly output, and our model runs stably out to, so far we've run out to 10 days, but we hope it would run out longer. So that's both of those are barriers some of the other models have not overcome yet. And we're in the process of we're going to basically the process of writing the paper, and we'll have a first version of the code out hopefully sometime this summer is what we're aiming for. But one of the issues with a lot of the current frameworks is there are a couple that allow you to train your own AI NWP models. So like the NVIDIA Modulus package allows you to do that with some of the existing architectures. But a lot of the groups have released their model, like they have papers. Some of them have released weights, but not code. Some of them have released code to run the model, but not to train the model. So we're trying to have something that's more open and community oriented and focused more on like kind of scientific investigation. But like the details of what that means is something we still we need community input on. So it's something happy to talk about more offline.
You got first, and you go second.
Will any file formats die in an appropriate way or only through a slow death like Genpack? Like, will there ever be a community saying like, okay, this is lived long enough, let's do the humane thing? Or will it always be slow and sad and crumbling?
In an idealized world, yes, there would actually be like a community like, all right, yep, it's been a good run, and let's move on. That requires conversation and thought, and we've not done that traditionally in our field. We just kind of add, right? But one of my adages recently at my own university is not doing more with less, because we're past capacity on that. It's actually doing less with less at this point, and doing less with less means probably fewer formats. And that may not be fewer initial formats, but fewer formats that are then the stored formats. That final curated format is more likely what it is, which then may be that more graceful way of not tripping and smacking our head on the ground, but tripping and recovering.
Thanks, everyone. I actually have a question for Dean. First, I want to make sure that I understood your point correctly. You said that for students, it's very important to see links between data sets and publications. Is that right? And is that what you meant? Is it from data sets to people who have previously published on those data sets, or to students' own publications on those data sets, or to both, perhaps? And my follow-up question is, for any sort of data sharing solution, what are the solutions we're looking at for creating those links between articles and data sets? So I'm here from AGU Publications. The way that we do this right now is by asking authors to cite a DOI for a data set in their article, which is a machine interoperable way to create these linkages, but also obviously has limitations in that authors don't always cite their data. I know there are people looking at other solutions. There are also challenges when it comes to accessing large data sets, complex data sets through APIs, of creating correct solutions. And obviously DOI prefixes cost money. So I'm interested in hearing, I guess, from Dean and from all the panelists about this challenge.
All right, I think the first question, so when a lot of my students go to Data Commons websites looking for data, they usually are looking for relevant publications as well. So we thought it was just a good idea to have a link, on the website. It can be categorized into different fields, specializations, or different areas, right? But we thought it would be useful to do that. The second question, I don't know if you want to take a crack at it.
Sure.
Yeah.
I think part of the challenge is that the days of the static PDF journal article should be behind us, such that with things like JupyterBook, and so you can literally build in the code through the maybe common APIs that we have to be able to access that data flow, such that then it's there. And we may have to collectively say that this data flow will be replicable for 5 years, and gives ourselves time limits, because indefinite in the future may not actually be the sustainable model. And we have to be okay with that in some way, especially with how rapidly all of our environments and our data are changing. And so how we do that, how we accomplish that even for a 5-year period, yeah, really good question. But
maybe another model to look to with this is Archive. They have the basically various extensions that are on the like you can either optionally turn them on or they're automatically on. Like they have linkages with things like Papers with Code and other websites where not just like the authors, but any user can upload links to code that go with the paper. Obviously, I don't know what the curation process would be for that, to have someone be checking that, which may be, depending on the scope of the effort, maybe a lot. But having something that where links to data or code or other supporting material for a given paper that can be updated on a like after publication as things evolve, even if it's by the authors or by other interested community members. It seems like the most sustainable path forward and kind of balance the like 5 years and it's gone or no guarantees. With especially for the things that like there's interest in maintaining it. I think one of the challenges is most papers there's quite a rapid trail off in the utility of the data and code, but then there's things that you can't predict which one that's going to be. So having some way to come back and correct and edit and keep it as a living document to some extent, I think is a key part of that.
Yeah, sticking with my theme on APIs again, if there was a packaging mechanism that was very simple, here's my data, I'll describe it. I've used this analogy before, but like the TurboTax interview, here's my data, answer all these odd questions about it, but then at the end it spits out something that you could put into an archive that was packaged in a way that it could be accessed through a standard API. Then all those products that people put in would be accessible. Hey, that Zenodo package is recognized by this tool and can be ingested live. So, having ways to make it not just, hey, I dumped my data in this pile and there it is, but it's a usable thing that's been preserved.
We have a question in the back, and then you.
Hi, Dean. I'm also from the Caribbean, so don't run away from me and we can chat later. So I think you brought up a great point about data silos. In particular, I don't know if you find this to be true as well, that you tend to have like this sort of Caribbean research bubble versus maybe a US or even globally research bubble, and there's little interaction between these two spheres. And I think that might actually be a great way to increase data sharing through collaboration, as well as making that data far more accessible across those different spheres. So what do you think about that?
Nice to see you. Yeah, and definitely let's talk after. But it's a cultural thing, right? Yeah. But more than that, I think the genesis of it is partly funding. Because we struggle so much for funding, so we want to protect data, we want to use it to get back some of that funding. So what personally I've tried to do with my research, once I generate data and get stuff published, I make it open access. Because one of the things I teach my students is the value of data is in its use, right? And not in its hoarding. So for me, it's about trying to change the culture, yeah.
Thank you. I have a second question for Kevin, actually. So part of, I think, the reason why data formats tend to be very brittle is also through the brittleness of the software and the packages that we have to use. So if you're used to Python, there was base map, then now it's CartaPy, and everything breaks because now everything is Python version dependent, and yeah, I mean, how do we solve the brittleness of data formats if the underlying packages that we have to use is inherently brittle?
Yes, no, very much appreciate that comment and the challenge of, is it the chicken or the egg, right? Is it our methods brittle because our data are brittle, or are our data brittle to some extent because probably a little bit of both, right? And may depend. Yeah, and that's one of the biggest challenges of working in these modern eras. There was a beautifulness to GenPack. It was self-contained. Now you had to get the data in that format, right? But then once you had data in that format, it worked because it was beginning to end all packaged together. But innovation was a real problem. It's that constant pull and tug of those different elements in order to do the active and evolving science that we want, right? We may have to accept some brittleness, but can there be a way to, limit it to the extent possible to then allow those things? And really, until we had package management within the Python ecosystem to manage all those, like, oh, I need CartaPy this and Pint this and MetPy this, right, to work together. it was really not accessible. And that's after we got that is when it really started ballooning our ability. But yeah, that is, maybe some combination of Docker containers and images or things like that to keep some of those more brittle things working for, again, whatever time limit we give ourselves to make sure that it works for. It could be a combination.
I had a question for MaKenna. I was curious in terms of formal data training. Have you received formal training at in classes through your internships? Like, what sort of skills have you picked up?
Yes. So for the first internship with the National Weather Service things, we had maybe 2 or 3 days a week where we had a mentor teaching us our studio. And then on the co-ops example, my mentor was also teaching me Python. So both like self-taught as well as direction from mentors. And as far as classwork, the only computer class I've taken was for C++, and I don't use that, so.
This one was for MaKenna as well. Great presentation. So I was wondering, you mentioned the common denominator. I'm wondering how large language models or machine learning, not necessarily like large language models could potentially help with that. I know obviously people use ChatGPT, Bard, and Find or whatever, but do you think, did you use some of that? Does that help sort of like level the playing field a little bit to kind of give you a little bit of guidance on things, or does it just make it more messy?
I would say, in my case, the machine learning and things like that weren't necessary. So if I'm understanding the question correctly, I don't think in my user case, the machine learning and things like that come into play, just because I, as a user, was not thinking about machine learning and AI and things like that. So, yeah.
So at some point, we're going to have to write a workshop report, right? And I heard descriptions of needs for data commons in terms of platforms. Here's something I can launch my Jupyter notebook on. And more of something I'd say is along the lines of a repository. Here's APIs I can access or data I can download or more data-centric. If you, for anybody who wants to take the question, if you had to rank or prioritize that, why, which aspect of that is more important for the geodata community, and perhaps why?
I mean, it's a thing. There's no right answer. Yeah.
I think one of the you kind of need both in some ways, because like even if you put all your data in a cloud bucket, you still need to the data needs to be downloaded, whether it's streamed partially or fully onto some kind of active compute system, whether that's also a cloud VM or your own like compute system, whether it's your laptop or giant HPC or somewhere in between. So there has to be some level of compute to manage that, and there's no avoiding it. So yeah, I don't think there's you can't have one without the other, unfortunately.
Just really briefly, because my experience on this is limited just to Earth Engine, and I would say that the direction that we're trending towards now is sort of exporting all the processing to the cloud, right? In terms of Earth Engine, Google servers do a great job, right? So we just write the script and the process runs over there. So I think that functionality moving away just from a repository is critical to the process.
Yeah, I'll just say, I think what we need to focus on are consolidating on the workflows that are working. Find the ones that scientists are coalescing around and support those. And it's hard to say exactly which thing is going to solve that. So kind of a modular approach where you're having pieces that can be applied, and that piece can be reused. And so, you know, because in a few years, is it still going to be Python? Maybe 5 years, it will be 10 years? You couldn't say that for sure now, right? So building things that have a durable component, recognizing they will have a shelf life, but really finding the pain points and working on that first. And then part of it too is, as these data sets get bigger, I mean, people mentioned this some yesterday, the funding agencies have to be involved to say, I mean, if you're talking about petabytes of data, you can't be using the same level of resources that you were before if you really want to take advantage of that. So actually having to spend more of the science money on that boring part of getting this data ready, it will actually pay off long term. But, you know, so those are my opinions.
We have one final question before our break.
Yeah, thank you. Mine is not actually a question, but to add to what Kevin said earlier on how brittle our codes are. Sometimes it's a trade-off between being more efficient, like an SCDF4 to an XRA. There is no argument that XRA is better than SCDF. So sometimes that's what happens. Thanks.
Thanks so much for moderating today, Jackie. Thanks to all the speakers. Let's give them all a round of applause. If the control room could put up the breakout group assignment slide. Yeah, that's perfect. So we have a break until 10:45, and then we'll go back to our breakout rooms. We have mixed them up today a little bit, so you'll be in a different room. Go ahead, Matt. Can you comment about it? Because you set it up.
Library C is the student breakout. So if you indicated you were a student or we somehow we put you in library.
All right, thanks, Matt. And then we'll reconvene in here at noon. So thanks, everybody. Do the takeaways real quick. So does library group C want to go first today? All right. I don't want you to have to go last every time. Yes, sorry.
Right, so we are the group in Library C, and there are a lot of the students in the group, and we had a lot of conversation about education and how currently antiquated some of the curriculums in the universities are, and a lot of things. There's nothing about data management, and how basic skills about the things like you have heard about discussion about course being taught in C++, and then when a lot of times when in the data commons, those doesn't work. So really the updating about educations and also fill those gaps in the current curriculums on how to use those data and doing analytics, and also the basic data literacy. So we did informal like polling in the group. 3 people know what NetCDF is, right? Out of the group of 10, a size of 10, and then different type data formats has been used in some level of geospatial data. Right now, it's not really like well included in some of the curriculums, and also develop and maintain and promote those training resources that can help the people to on-ramp into those systems and use those tools, especially those easily discoverable, right? You don't having 1,000 different notebooks is not going to be help anyone if you cannot find the most relevant one for you to use and directly. And for the commons, really need to be aware of those multiple entry points and understand who the users are and then what the level of experience they are, and providing the right on-ramp and to help them to get into the system, use the system the most effective ways. And there are other things mentioning about the citing the data. I think a lot of data providers would be happy to see that mentioned and then make it easy to do that. And also, one thing is the community aspects of it. How can we create data commons that provide a forum and that people can contribute back, and for how they are using those data. And oftentimes when we're creating a data set, it doesn't, those data have the life outside of the intention that we have for our specific users, and people find ways to use that data in the most creative way. So we should provide a place where other people can share back and say how they use those data, and this is how we use it.
Okay, I think we know how we're going. So library group B.
Cool. All right, so our main takeaways. First one is there's a full spectrum of different users, use cases, and requirements that need to be fully accounted for. So this spreads out to academics, scientists, the social sector, the private sector, and so it's a wide berth, right, of different things that need to be accounted for. We also did talk about things that are created do need to stick around for different various reasons. So that's another good one to think about as we're going through all of these things. Partnerships with the private sector and different institutions are required to accelerate this work. We also focused a lot on the importance of community building. And this is a two-way communication. There needs to be a give and a take between the user community and the developers. It should be emphasized, incentivized, and encouraged. This really, helps promote new technologies and solutions, and also, furthers the understanding of those technologies and solutions. Metadata curation and maintenance is difficult as that data is manipulated. There's an importance of data provenance. The value in the data is in its use and its applications. So identifying the potential users and communities is paramount to making sure that data can actually make an impact. And how we cater to the different needs and requirements is going to be different to our point at the top there. And lastly, we need an open, centralized platform that includes different agencies, the private sector, different institutions, that includes scalable compute resources. We also need to make sure that the data is findable in those as well. So.
Yeah, this was a great summary. We talked a lot about also like how we can better partner up with like private sector, and also how we can provide a centralized platform for all the data to be findable, similar to what GitHub has. Somewhere for all data set, and the data itself can be hosted on like premises, even like on different institutions, but somewhere for the user to find like a catalog, or somewhere for the user to go and find the data. So yeah.
All right, thank you. So library group A will be up next.
Thank you. So we kept our bullet points just 2 bullet points, and we did that by cramming all of our barriers into 1 bullet point. Yes. So we started off with a really interesting discussion about what we're calling cylinders of excellence, which are these domain-specific, infrastructures or systems that have been really successful for their domains, but are also a little bit siloed. And that we need to recognize that those have emerged and exist for a reason. They're doing good work for their communities. So we need to think about a couple of things. One is mechanisms of governance across them to develop common standards and expectations. We talked about whether there should be a hard governance where people make requirements, or more of a soft recommendations, best practices kind of work. And for efficiency, looking across these cylinders, you need to separate where those cylinders are meeting unique needs of their communities, which is great, where they're meeting common needs and there's a lot of duplication, where perhaps you could have common building blocks to meet those. And the more common case where it's tools that are mostly meeting the same needs, but everyone's got a slightly different. So you would need to do some work to create a tool or building block that spans those. We then got going on barriers. So data access and storage is clearly a barrier. Accessing data across different clouds. Somebody raised the conceptual idea of, an HTTP for data, make it that easy to grab the data from whatever cloud it's at. Authorization, authentication, logins are a barrier. The incentive structures for community work, as well as the kinds of credit schemes for contributing to open source code and building blocks need to evolve. In a lot of cases, the new contributors to these open source communities lack the confidence to feel like, yes, what I am creating is worth sharing, is worth using, so we need support and on-ramps for that. We also talked about the idea of off-ramps. There are never adopters, people who are not the early adopters, not the middle, but like they have their thing and they want to use it to the end. They're part of who we need to support, but are there off-ramps for those users, but also for systems? As we develop systems, even at the front end, we should be thinking about how do we get out of this, when the world changes and we need to move on. Universities, academic institutions in general don't support operational infrastructure and the work behind that. We have cybersecurity concerns with all these open source building blocks. We need to make sure that they're all solid. They're not creating backdoors into our systems. We need more general training in the science community about data science fundamentals. And we also need to be better at articulating the value of our work. Somebody at the table said you need to stop calling yourself like the plumbers. You're not creating the plumbing, you're enabling groundbreaking new science or whatever your pitch is. So that's what we had. Thank you.
Okay, next library groups. Main seminar room.
Thank you. Yeah, so our group had some overlapping points and some other points as well. One of the first main points that we had was that there's a lack of data and metadata standards in some communities. And one potential solution to this that we discussed was organizing more workshops involving experts within those particular domains and communities, and that can lead to standardizing metadata specifications, as well as more education and outreach. We also had a lot of discussion generally on metadata and that it varies significantly. Some potential solutions that we were discussing in regards to that point were that we should really be encouraging editors, reviewers, funding agencies, and private players and communities to enforce but not necessarily mandate data availability and metadata standards. We were definitely highlighting having reviewers that know their domain well, being heavily involved in reviewing and checking that data is accessible and has the necessary metadata. We also, on this topic, wanted to be mindful of data sovereignty and value data curators and communities who create and maintain useful packages, whether that's incentivizing through the higher ed structures that we have or other communities. We want to try to place more value on those efforts. We also discussed a need for data and software persistence and permanence and guidelines regarding those topics. We were discussing DOIs as really helpful for data permanence and that notebooks are really useful for software sharing, and that at least even if sometimes the code isn't necessarily running completely smoothly after a little while, that at least having the algorithms for how people did their work can be really helpful in order to enhance reproducibility. We also discussed that we have a lot of data and that it's helpful to continue to prioritize which data we actually want to store and keep. So that was just a different perspective that was added to this conversation, that we may not want to try to keep everything, but to be somewhat discerning in what we are prioritizing storing. And then some other desired capabilities that we wanted to highlight were some existing compute capabilities such as NSF Access, OSPool, and NAIRR, automated metadata generation and maintenance. So there's Sparrow as an example that came up for field observations that sort of automatically, it's a tool or an app to automatically generate metadata. And then publishing light pre-trained and tunable ML models also seemed important within this group. We also talked about how do we interpret data and its context, and that having community forums, Zulib channels, help desks, and links to papers readily accessible next to the data sets can be really helpful. And then support for data approximate computations is lacking or minimal. There were some other tools that we shared there. And then our last point was visualizing and stream without downloading the data can be really useful in order to be able to decide what data sets you're going to look at.
Thanks, Tegan. Okay, Chapman.
Yeah, so Joseph is losing his voice, so you're stuck with me. So I'm just looking at some of the other break room sort of topics, and I'm kind of seeing commonalities and threads, but we're just using different words, but we all kind of mean the same thing. So number one was community. Is having community engagement more. So communities recommending, inviting, and encouraging key funding people to attend, to sit at the table, to be here. People were commenting, where is NSF? Who's sponsoring this event? Like,
they're online.
There are? Oh, hi. Hi, Nick. Great. All right. You don't know who I am. The second topic is who funds us matters a lot. You know, they are our bread and butter. So the community, and who is our community? Well, it's our scientists, our users, our educators, and our scientists. We need a business model either to create or improve or develop a business model to support the infrastructure. And the infrastructure are our people, our storage, our computing resources, the protocols, but also in particular, what was mentioned is a longer life cycle of funding to be sustainable. So there's the research part of it, which is 3 to 5 years, but to build all of this stuff really takes quite a bit of time, and it's an iterative process. So it's an elastic process that grows and grows and grows and balloons. So these apparently exist. Some of these models do exist. So what we could do to kind of advertise this is to create a governance council around the data commons, and that functions independently from the research needs, so that we can address more, data commons needs as well. And then the third topic was needs. Now, some people can call it barriers. I've decided I'm going to call it needs. Some people might want to also call it opportunities. One of them is simplifying and unifying data needs and uses, portability and interoperability, many different sources. Can we have, it's like that Buddhist notion, many paths, one road kind of thing, lead to run one road. The need for facilitators with a well-defined expectations and scope of service, because we can't do everything for everyone. So a targeted approach as to who we want, who our user base is, and how we can serve them better. Documentation and education, so that I see that word metadata bandied about, so that's what we mean. We mean better documentation by the data providers to tell us about their data, what went into taking their data, how that data was transformed, so that we have an understanding of what we're using our data for, and then we have a better idea of, when we do our research and our summaries, the trustworthiness of that data. And then, of course, needs is money and visibility. And within that visibility function, we have website, knowledge space, where to go for help, ambassadors, and chat box. Oh, and I forgot above that, prioritizing our needs, right? Because someone said we're doing less with less. So can we do less better? And tailoring those needs to the user expertise. And finally, in the needs is standards and compliance. And I think that's also a theme that has been running through some of the breakout sessions, standardization, and compliance. And then, of course, the researcher in me, I like to think of things in terms of equations. And so the first speaker, Kevin, you talked about the brittleness. So what's the opposite of brittleness? Well, that's durability. So it's like, how can we create durability? And as a scientist, I like to linearize everything. So there could be like a squared in there. And I just realized I forgot to add a fudge factor. So, so durability, we said, would equal the data plus the tools plus the support. And to qualify that support, we have a function like cybersecurity, community input, and as well as specialization. So that's mining that expertise. And then, of course, we came down to specialization and community developed design. So there are use cases that exist that are successful, and can these be used as a model to drive other data commons that are created or data commons that exist out there in terms of helping with data accessibility and whatnot. So that's all we got.
Thanks, Jackie. All right, I think we have, let's see here, a couple more. So Damon. And then we'll break for lunch right when we're done here, so.
The last one? No. Oh. Sorry. We had a lively group and a lot of good discussion. So we started out talking about data deletion policies. I think because Rachel brought up that nobody else had really addressed this so far in the workshop. So clearly these are things that need to be defined and need to think about who defines them. We talked about model data is something that theoretically can be recreated, but observational data, probably not. The notion of common denominator really resonated with people. Clearly this is desirable, but not sure how it's achieved. This is something that I think would have been fun to dive in deeper if we had more time. Maybe it's a topic for discussion on Friday. Culture change and new business models. Culture change is something that we all feel is probably needed. And some of this is in response to some of the new business models that exist, like, for example, around commercial cloud. So this presents challenges both for centers and for the scientific user community. Also noted that incentive structures in academia probably need to change as well. Pace of change is overwhelming. I think everybody agreed with that. How do we deal with it? One suggestion perhaps is containerizing environments and then freezing them. So we know that and this is with respect to a data commons, can we make some effort to better support reproducibility? The speed of innovation, especially in AI, is moving faster than the research to operation project life cycles. We heard DJ talk about, there's no agreement on what AI-ready data would look like. And something I hear a lot, scientists simply don't have the bandwidth to keep up with all the change. And then lastly, we talked about unmet resource needs for infrastructure. Many of the challenges that exist, we feel like there's potential ready solutions such as data format conversion, but finding the programmers to address these needs or finding the funding to support programmers and other people to address these problems is problematic. It's not something that the funding agencies tend to support, this type of work that may be considered drudgery, but is vitally important to the scientist.
All right, thanks, John. All right, 680B, you're the closer today of 680B, you're in here. If they're not, Egg Belly or Riley, are you in here? If not, we'll, oh, he is. All right. This is a good one, legacy data formats. I'll just read through them real quick.
Come on. You're the closer, man.
Am I the closer? Okay, great. Let's let's close this out before lunch. This is me, right? Yep. Okay, how do we handle legacy data? Okay, so keep providing software handlers. So that's so the interfaces are virtualized interfaces like ZAR. I think people were talking about ZAR and stuff. Let the data formats, since software can be cheap, but requires maintenance. Instrumentation still a potential problems. There's a lot of proprietary formats with instrumentation, so you get stuck into, proprietary formats that are difficult to figure out later, because data usually outlives, what was the term? I think the data usually outlives the software, if you will. So we mentioned solutions could Kerchunk or ZAR solve some of these problems, common tooling, language that's agnostic, and it's sort of self-describing. That's the first time I've learned about ZAR, so I thought that was interesting. Difficult to predict, so the tech changes, things keep changing. I think we were talking about Weka, which, they have cool swag at SC. That's the only thing I know about them, but they're new technology. Use communities to describe workflows, higher level post-processing. Pythia is a great example because they have example notebooks embedded in the embedded expertise that can expose data to new users. And then I think ECMWF, they were talking about another system. What was that one called? Wikio? Wekio? Yep, that one with ECMWF, which is another great tool for exploring data. Providing raw versus processed data. Raw data is basically practically useless. Very high level data is too bespoke, so they had like this chart on this curve, but maybe a little in the middle ground that enables innovation for end users, and multiple organizations that can do this, but which one? I guess we're going to be biased and say NCAR, of course. Publishing storage solutions, short-term versus long-term storage. And when you go from short-term and then you go to long-term, they tend to be harder to find when you move over to the long-term sort of data storage. Need support for embargoed access. So I guess certain agencies, they embargo the data before it gets released or it gets released to the public, whereas I guess NSF and some of us, you just release the data and it goes out immediately. Also, different sizes of output are sort of issues that we're talking about for publishing storage solutions. And that's pretty much it.
Cool. All right, thanks to all the moderators and note takers again. Any quick announcements does anybody have to make? Otherwise,
and everybody who's going to the Damon room, follow me.
All right, and otherwise we'll reconvene at 1:30. So thanks, everybody.
Good afternoon, everyone. We're going to get going in a second, and I know we had some wonderful lunchtime conversations, but they need to cease because we have another jam-packed afternoon of same format, 4 plenaries, 15 minutes each, questions at end, and then breakouts afterwards. I'm Scott Collis. I'm from Argonne National Lab, part of the steering committee here, and I was just commenting to Doug this morning, the wonderful diversity of folks we have here. In each of the different breakouts has been fantastic. But our first presenter will be online, and it will be Asti Bhatt from SRI, who will be presenting on data curation needs for large and small NSF facilities. Asti, can you hear me, and are you ready to go? Asti, I think you're still on mute. Yep.
I can hear you.
Perfect, and we can hear you. So Lee, take it away.
Okay. Thank you so much for inviting me here. And I'm sorry I'm not there in person and missing all the wonderful discussion. We can thank the weather gods. My flight got canceled yesterday, so I have to do it online. So my name is Asti, and I am the PI of 2 NSF facilities. One is a large facility called Advanced Modular Incoherent Scatter Radar, or AMISR, and the second is a small facility called Mid-Latitude Off-Sky Imaging Network for Geospace Observations, or MANGO. I am an ionospheric scientist by profession, and I'm going to talk about a perspective from the data provider on data curation needs for large and small facilities. I will also talk about how we as project is managing this and how we are working with the community data facilities that are not managed by us as projects and how that works out. So I'll first focus on the large facility, that is the AMISR. And even when I say a large facility, AMISR is really two different facilities which both have the same purpose. AMISR has two radars. One radar is located in Alaska, another located in Nunavut, Canada. These are both remotely operated, electronically steerable radars. They used to provide most accurate ground-based measurements of ionospheric state parameters, which are electron density, temperature, velocities, electric field. They are both standalone facilities, and they have standardized data acquisition, processing, and sharing. The facilities are quite old. They started operating in 2007. The type of data that we provide are two types. They are both spatially resolved parameters and in time. So on the right side, you see this map of different dots. The different dots are different beam positions that come from the radar. And in each beam position, we have a time series of state parameters like electron density and the temperature and the velocities. This data, for example, is from the last time we had a huge solar storm. Some of you may have seen the aurora from wherever you are, or at least seen the pictures in the news. So this is what our radars observed at that time. Like I said, these are two similar radars, but also two different because of the logistical constraints that are at each site. The radar located near Fairbanks, Alaska, is connected to a power grid for operations. So it provides 24/7 data since 2007. Total is about close to 150 terabytes of raw data we have collected. The other radar, the one on the right, is the one located in Nunavut, Canada, which operates with its own diesel power plant. There is no other type of electricity or source of electricity that exists there. So the data generation is quite intermittent, and the local challenges make it difficult to operate the radar all the time. Coming to how we are curating and sharing the data. So the key thing is our mandate is to ensure that data are distributed to the community. And for that, we need to ensure the data are transported and ingested properly. Once again, since Poker Flat radar is in Alaska, connected to the grid, the data arrive instantly. The data in Nunavut, the data arrive about 1 to 2 months after the operation via snail mail, hoping that it clears the customs. We calibrate and process the raw data into derived parameters using the software tools that we have developed. These software tools also need maintenance and update regularly. And that also leads to a challenge of data versioning that I'll get into a little bit later. We do the backup of raw and processed data in local network storage drives and Amazon Glacier. We maintain these data storage drives, servers, software. One of the most common requests that we get as data providers is reprocessing of old data that were taken in 2007, 8, 9, etc. So we need to maintain all of them, maintain the associated metadata and raw data. And when I say metadata, I mean how the data were processed, what parameters were used to process this data. The total size of processed data becomes quite small, as you can see. And we share the data using two repositories. One is maintained by the project, and one is maintained by a community supported common location. It's called the Cedar Madrigal database. That is a repository for the geospace data from various instruments. The Cedar Madrigal database, this is on the left here, that was built to share the data from the radars. But when the Cedar Madrigal database was conceived and built, the radars were only one type. That is, they would always look in the single direction at single time point. The AMIJA radars look at multiple directions at the same time point. And so that makes the format a little bit unintuitive, but it still works just fine. The other database is maintained is by the project, and this is, again, both the data repositories provide the data in HDF5 format, but with slightly different metadata, just because, again, Cedar Madrigal has its own metadata maintenance, while the project database, we often add things which are not necessarily part of the Cedar Madrigal metadata. We provide common visualization at both repositories. The data citation rules are similar, that we contact the PI before please contact before using this data. However, that is not always followed, and that is generally the function of how the community typically looks at such large facilities as their own, and think that most people feel that they understand what's going on, which is a little bit tricky. Switching gears a little bit to the small facilities, as Mango, it is a collection of different instruments. Well, they are the same instruments, but they are distributed much more than the two radars I mentioned. And so there are about 15 different sites. Some of these have the cameras, and some have these interferometers, which are looking at the same nighttime emissions, but also to derive the wind speed in the upper atmosphere from the measurements. The project came after collaboration between two instrument PIs, and that also is a part of how this is different than the NSF large facilities. The data acquisition and transport is standardized across the instruments. Here is an example of the data, again, from that same auroral storm that you all saw in May 10th and 11th. This shows the extent of the aurora all the way down to the Florida and Arizona, and the interferometers are measuring what the wind speeds were like at that time. So this is an example of the visualization that we can provide, or can be created from the data that we provide. The data products are shared via 2 or 3 different places. There is a project website that we share the imaging data. There is the winds, the vectors are shared via the different website, which is by the instrument PI who has had this type of instruments in other parts of the world as well. A common point to note that the data transport system between AMIJA and Mango are the same, because again, developed by the same skilled programmer. The wind vectors are also shared through the Cedar Madrigal database that I just talked about. All data are provided via HDF5 format and PNG format, but the Cedar Madrigal repository is not suited for imaging data, for displaying or downloading. We back up all the raw and processed data on the project-owned servers. Again, same rules of the road for sharing. We just contact the PI before publishing. And the software are all open source that can be used to create any such visualization. None of the users need the project to share the visualization. They can all be made by open source tools. So what are the common challenges that I find as a data provider between these two facilities? We have no standardized way to create citations for continuously streaming data. The thing that is common between these two projects is that data are continuously streaming. So every day, every night, there is a data source. So one can assume that we can have, a DOI for every night of the data, right? But then people often use large data for a whole year, for multiple years, and that gets very challenging to create any citation for. The community repository, that is a CDR Madrigal database, it provides persistent URLs. That is, for each data file, there is a URL. However, the data files are not standardized because they are not each data file is say 1 day. Some data files are multiple days, some data files are 1 hour. That gets into the challenge for how to create proper data citations. We rely on users to contact us and acknowledge the award number in publications in order to make sure that, again, A, the data are used, interpreted properly, and B, that we know who's using the data. The other challenge is there are no standardized metadata for the HDF5 files. There is a set of metadata that the CDR Madrigal database uses, but they are not standardized or calibrated across various instruments. So it is hard to compare the same quantities between two different instruments. But this is a project in itself. The instrument PIs provide their best guess for metadata and update it as necessary, which is also a factor in the notion that we don't have standardized way for data versioning. We can upload multiple versions of data on the community data repositories, but it is difficult to effectively communicate to the users what changed and why it changed. For example, for our calibrations in the geospace community, one of the things that changes is the angle of the magnetic field. Now, what you thought was magnetic field in 2007 is no longer. You're not looking at the same direction as you were looking in 2007 when you think you are looking up the magnetic field lines. And so that means many things have changed. But communicating this sort of thing is very difficult, and I can get into the details for whoever's interested. The learnings from all of this is that, as I mentioned, the challenge is to provide the continuously streaming data processed in a consistent manner and adhering to fair practices with limited resources, because everything that we do requires skilled people. Software, data, servers, maintenance, update, everything requires skilled labor resources. Maintenance of this entire data transport system is non-trivial, and it needs to be maintained. Otherwise, we don't fulfill our mandate. The new challenge is to create the machine learning ready data sets from this long-term data. We know that in order to make sense of this large data set, we need to use some modern data science methods to actually, at the very least, categorize, classify data into different buckets so that we are able to make sense of all these different buckets. And scientists can focus on, okay, well, this is where you saw huge solar storms, which were like this. This is where you saw quiet conditions, things like that. But because these are continuously streaming data, you always need a human in the loop to make sure that the data are clean and curated properly for ingestion by the machine learning algorithms. This is, again, non-trivial and requires skilled people. Again, as a data provider, in the last point I'd like to make is that I would be extremely happy and willing to outsource all the data curation and sharing to a standardized data repository that is maintained by NSF, for example, and process that can store raw data, process data with version control, and has a DOI citing authority. This again it should not require each funded project to maintain their own set of skilled labor forces in order to do this, something that can be standardized. So thank you very much for listening to this, and I'm happy to take questions at the end of this thing.
Are we back on? Yeah. Thank you very much, Asti. And given your remote, that was like perfect timing too. So our next presenter is Andy Newman from, I know I have to say it now, NSF NCAR.
I'm fine either way. I guess I do have a collar that I can attach to. So this is, if you have the joy of working in Boulder, you get to dress down most days.
This is dressing up.
Yeah, it's close. Yeah, it's close. A collar, yeah, and pants, no flip flops. Yeah, sorry, I'm cutting into my 15 minutes already. Yep. So yeah, so I'm going to talk about what I do on the data production, data producer side, but also, I guess, some perspectives on the user community side. And I was unable to attend yesterday, so I don't know how much that's been talked about. It's been talked about some today, but I'll try to weave some of that in as well. So I've had some really nice experiences in my life to think about how you introduce yourself differently, so I'm going to do that. I grew up in Minnesota. I was always interested in the weather, so I'm what you would call a weather nerd. But weather nerds don't really, I don't think, appreciate what it takes to run the weather enterprise. Right? You think it's all storm chasing and hurricanes and cool things like that. So when I got to school, I actually then realized there's a lot of math and physics and computer science. So then I was always actually interested in radar meteorology, so I started working with radar data, field campaign, rain gauge data. That's actually a video distrometer from my master's degree up in North Dakota. Lots of snow. You can see that's two-foot snowdrifts there, roughly. Anyway, so started learning about data, what it takes to work with data from the user perspective, and then as I moved on in my career here at NCAR, I was lucky enough to have a postdoc here, and then I've now transitioned to a project scientist in the research applications lab, where I do a lot of water cycle hydrometeorology work and produce a ton of data. As the Doug and the RDA folks know, I have several outstanding requests with the RDA. No fault of their own. It's mainly on my side at this point. Yeah, so I learned about what it takes, right, to provide, produce, and then archive usable, useful data for yourself as a researcher, but then also for other folks. And so a lot of the things that I do now are continental scale, so like large domain, large data volumes, complex things. Could be grids, could be watersheds, and these are just points to represent watersheds, right? But it's not traditionally gridded, right? It could be an unstaggered grid. It could be just polygons of a watershed aggregation. It could be vector, right? Like a river reach, right? That's often represented in a vector type format. And there's like graph, right? You need to know what stream reach is connected to other stream reaches. So there's things like that come along with data. So right, multidimensional complex attributes. What are the underlying data that went into this fusion product? So this is like a mishmash of, say, 10 or 15 different observational data sources. So then how do I, as a data producer, keep track of that? Then how do we keep track of that when we go to archive it? It's pretty challenging. So my work, as I've kind of said, is primarily focused on actionable science, and so I like to think what we were doing in the research applications lab was actionable before that became this phrase that was used widely. But it's really good to see the emphasis on this, because I think that really motivates all of what we do and then supports fundamental research in a two-way kind of conversation. So again, yeah, I'm often involved with complex interdisciplinary projects where you have a really high need for useful and usable outcomes. So like it's sponsor, operational agency driven, like Bureau of Reclamation needs to make a decision on, are they gonna raise Oroville Dam because of climate change? That's a potentially 100 million type of infrastructure decision, right? Real dollars. And so that's the kind of things where these data end up, which I think is really motivating. And hopefully that's, a goal for a lot of what we do. I think we heard in some of the breakouts, the value is in the use of data. And so how do we take complex things like these climate grids, the stream flow network there, even temperature on similar networks, how do we deal with all of this? And I'll keep speeding up here, hopefully. And again, so my perspective is historically centered on geoscience researchers and application super users, accessibility first. So like the big agencies, the high technical folks, but recently starting to realize there's a lot to accessibility, equity, and other issues from the community perspective. Climate change along the Arctic coast is an everyday thing, right? Like community managed relocation, resilience planning. How do they get access to the data they need to write their climate adaptation planning that they need to have to get any grant money to actually do anything to deal with climate impacts? So how do we enable that from this data commons perspective? So things that I've been involved with either as PI or actually making the data, a lot of regional physical model simulations, so regional climate models at fairly high resolution. This is an ongoing project that we have, right? So we have climate data on grids. We could represent it as watersheds. We have atmosphere, land models, river routing models. All of these have different data streams, different representations on the grid or subsoil levels, the vector data. And then you may want to have different spatial aggregations, temporal aggregations on top of that. And then kind of in the similar vein, but I broke it out differently, is because it's maybe a little simpler to deal with, is often we also do a lot of statistical models, but then this adds often a different dimension of ensembles. So again, it's just another way to think about multidimensional complex data where you have underlying global models, so like CSM, EC Earth, CAN-ESM, and the numbers are specific ensemble members from those CMIP 6 class models, right? So this all needs to be tracked, and hopefully we're doing a good size on the production side, but also then that needs to be searchable, discoverable in the database, because it's very important for an agency to know that if you're comparing something with a different method, it's apples to apples. So if you're familiar with climate model simulations, R1, I1, P1 is meaningful, and if you go to R2, I1, P1, that's a different thing, right? And so if you try to derive information from that, it has different outcomes potentially. And then where I started and still have a fondness for is like these observational based data sets that kind of maybe demand longer term preservation and a little bit different aspects. And they could be model observation fusions and other different things, and so just different kind of flavor of complexity. So as far as user communities, I kind of am taking this tact of what I've served on our projects is, again, a very wide range of users. And I think this user community has only been growing as the need for data in the data-driven world, data-driven economy is increasing. So like historically, again, super users, federal state agencies, universities, individual researchers, and like just an example of analytics from a data set. This kind of information for me is super useful to justify my existence, right? But I understand this could be a barrier if you have to have a login, anonymous data versus login information. But even just the ability to somehow track where people come from, to go then back to my boss and sponsors, right, on your performance evaluation and funding agencies. It's all important things to have. And yeah, lots of agencies use our data. And this is just to highlight again, like most of these folks have really high technical capabilities. So like from a common standpoint, I don't worry about these people at all, because they can basically take whatever we throw at them and adapt, right? This idea of like the legacy data and changing access and things over time scales is interesting to me, because the legacy data exists and the legacy methods exist for a reason, because the operational agencies have very little bandwidth to change, right? They're worried about raising the gate on the dam to prevent a dam failure, for example. Then thinking about, this shift to community-wide and equitable access, it's all resource constraints, time constraints, people constraints. How do we, I think it's really important for us to think about how do we help enable data to get to where it needs to go in an easier way from where we are now. And it's not I don't know what the solution is, but it's just something that I think we should always just kind of think about, right? And they have different needs depending on where you come from, right? It might be, I think I'll have more in a little bit, but just to, again, highlight that there's resource constraints on every facet of not just us, but on the user side as well, that we hopefully can try to address when we move forward on this. Right, so again, like I don't worry about these folks too much. They also know where to find you, and they're not shy about reaching out, right? So they're always, first served, first to come, first served kind of thing. But then when you start to move downstream, we need to be able to enable, maybe the Commons isn't the place that does all of these things, but we need to enable all of these things, like subsetting, aggregation, right? The compute with the data so that you don't put it on the user. How do we do searchable, explorable, interactive data sets? How do we keep with the data comprehensive do's and don'ts, all the different things we need for metadata, discoverability of other relevant data sets, right? Like even for somebody who has a PhD in atmospheric science, used to do a ton of technical work, right? It takes a long time to find, as we've talked about, all the data you need, right? And so you generate these huge spreadsheets, and that takes hours of time. And why are we still doing those things? I don't know. And then still, like, if people want data, how do we get it to them, right? Cloud is great, but bandwidth is a limit. So do you ship hard drives, all these other kind of alternate methods that we have to think about and do. I remember shipping hard drives during the pandemic with nobody around, which is kind of weird. But so yeah, then even less technical, right? Like maybe you only have Starlink a few days a week. How do you find our data and derive use from it? Again, we need to think about how we enable all of that. We don't necessarily need to do it here, but I think just thinking about how we enable it and keeping all of these explanations and limitations and correct usage, all of these things that on the science expertise side, we need to do a better job doing, but we also need to then have folks help us on the curation and management side. So there's multiple handoffs in this kind of chain. Yeah, so I'll just kind of give an example of like what I've run into in Alaska is a really nice example of like a handoff, right? That could leverage the data commons. So this Northern Climate Reports is funded by the USGS Climate Adaptation Science Center and probably some other folks that I apologize, I'm forgetting. But it's really cool. It has a searchable, like interactive map that you can click on your points, and you can get all sorts of information about what data sets that they've been able to collect and be aware of from a climate change perspective. So it has different river data, it has climate data, it has ecological data on historical and projections, as you can kind of maybe see here. But you can do all sorts of cool things and get just essentially layperson reports with, you don't need a lot of bandwidth to say how climate change might impact your watershed, your place. So how do we work with folks here to make their work easier and then keep the handoffs happening to the end users, whoever they may be. So my wish list, I think I've hit most of these points, but it's always good to keep hitting them. From my perspective, it takes me a ton of time to even just understand where data is supposed to go, what the expectations are of who's paying for it. Am I going to pay for it on grants? Is the repository that's supposed to take it even technologically capable of taking a data set that we've generated? We've been pushing the boundaries on some of the technical capabilities of these of repositories to how do you deal with 300 years of climate data on a 4-kilometer grid that has 100 different fields that could be relevant to different research and user communities. Talking to our bosses and our program sponsors, how do we normalize the expectations that are being put on everybody, and how do we, I guess I loved that phrase, do less with less. It really, I mean, I love it and I hate it, I guess, already. It's hard. You always want to do more, right? And that's what you lose sleep about, is like, oh, how can I help get more stuff done? But that's not necessarily good for your mental state. And these concepts that I've been hearing, levels of service, we talked a lot in our breakout group about Google Earth with the free access, and then you can pay to play for more. But how do we maybe open that up more with different levels of archival and service, and then all the metadata and discoverability? How do we keep all of this information that we need to keep to have proper use, to have guardrails for proper use, right? From the ethics side of science, and these are not my original thoughts, but like somebody who produces data, I don't want it to be used incorrectly and then have decisions be made incorrectly. I think we should all, hopefully, are all worried about that, but not too, don't like stress yourself out too much. But like, it's something that you should always be thinking about. And so how do we keep that going? How do we like enable that from a commons to make sure that the end users kind of know where everything is, what is the use practices, et cetera. And then again, how can we always think about equitable access, which, I admit I have not done a good job of this in the past, but we got to start somewhere. So, and I think I can just leave that up there. Am I on time here, Scott? You are spot on. Perfect. Great.
We'll do a microphone fist bump. So, thank you, Andy. Our next speaker, who, please correct me if I mispronounce this, is Katherine Cariglia from MIT's Haystack Observatory. Did I get that right? Cariglia. I'm sorry about that. And I'll hand this over to you.
Thank you very much. Hello, everyone. My name is Katherine Cariglia, and I am an undergraduate studying computer science at UMass Lowell. And I started working at the Haystack Observatory when I was in high school, and I primarily focus on maintaining the Madrigal database. And today I will be talking to you all about how Madrigal provides data to users, how we organize this data, how we facilitate data discovery, what challenges we face in this, and how we address some of the challenges and needs that other folks have brought up throughout this workshop. So before I get into Madrigal, I'll talk a bit more about CEDAR. So CEDAR, which stands for Coupling Energetics and Dynamics of Atmospheric Regions, is a research community investigating the near-Earth space environment. And Madrigal serves as a community resource for atmospheric science data from various ground and space-based instruments all over the world. The Haystack Observatory Atmospheric Sciences Group maintains the Madrigal database, and Madrigal itself is part of the Millstone Hill Geospace Facility, which is supported by NSF. Thank you, NSF. So Madrigal itself is a distributed database which is installed at various sites around the world and has a central archive at the CEDAR Madrigal database. Data at each site is controlled locally, but metadata is shared between each of these sites for easy data access. So say, for example, you could search for GNSS total electron content data on the iSCAT site, but you will be automatically redirected to the CEDAR site. So what kinds of data does Madrigal have? Like I said, we have a very wide variety of ground and space-based instrument data, including but not limited to incoherent scatter radar data, photometer data, in situ satellite data, such as the DMSP satellite data, meteor radar data, and of course, GNSS TEC data. This is our most popular data set, and pictured here is a summary figure of this data, which we try to include for all of our experiments stored in Madrigal for each instrument. And we work with the PIs for each instrument to create a summary plot that best characterizes that instrument's data. Madrigal is open source, both the database and the web services API. You can download your own version of Madrigal here after visiting this site. The current version control system that we use for Madrigal is Subversion, but we are very interested and currently trying to make some progress on porting this over to GitHub so that we can introduce community contributions, like issues, etc. And so how is data stored in Madrigal? As Asti mentioned earlier, the underlying data format for each file in Madrigal is HDF5, and each of these data files have well-defined parameters with standardized descriptions and units. Additionally, all these parameters have corresponding uncertainty parameters, so you can determine the accuracy of the data you're looking at. Missing and assumed values are always included, and these well-defined parameter standards allow for the existence of a derivation engine to calculate any desired parameters you may wish to see in your file given a geographic location and date time. So say, for example, you could calculate the shadow height if you so needed that. And this allows for the data provider to not have to manually include these parameters. So, as I mentioned, the file format for each file in Madrigal is structured HDF5 format with generally self-describing data, again, including all the parameters, units, notes, and definitions. The table layout for each data set is always given, and the array layout is default if any independent parameters for the data are given. So say, for example, just to sort of I wish I had a whiteboard, to visualize the table versus array layout, if you had TEC data, you would just have, say, the latitude, longitude, and the TEC all in rows and columns. And in the array layout, you would have a grid of latitude, longitude populated by those TEC values. So how do we organize this data in Madrigal? For each Madrigal site, the highest level of metadata is the instruments stored, or the instruments with data associated with them, the experiments associated with that instrument, which are limited duration and have a single PI contact, the experiment files associated with the experiment containing data from one analysis of the experiment, typically over 1 day, but can change depending on whether it's a long-term experiment or limited duration. And of course, in each of these files are individual records containing measurements over a single period of time. So, on to the derivation engine. Of course, the standardization of these file parameters for each file allows for the existence of the derivation engine. And again, all of these parameters have corresponding uncertainty parameters, so you can always know how accurate your data is. The independent parameters are built into the standard, and the derived parameters always appear in every file. The derivation engine itself determines which parameters can be derived, and you can implement new derived parameters using either C or Fortran, and work is in progress to calculate more derivable parameters using Python. So to access Madrigal, you can either use the web interface, which is best for discovering new types of data, or you can use the Web Services API, which is available in Python, MATLAB, and IDL. The API is particularly useful because you can download your files quite a bit faster compared to the web interface. So as opposed to downloading just one file at a time, you can just automatically download your files just using a single command. And you can even filter your desired data by which parameters you would like, which derived parameters you would like, and over what time period you would like. So, data reproducibility. Madrigal files are never deleted. They are always archived. And when a new version of an experiment file comes along, the old versions are marked as history. Every file has a citable URL, and the Python API even allows for the creation of a single citation for multiple files. And from the data download page, there is a very handy-dandy button where you can automatically cite your file, and here is an example of a citation that was generated. So these DOIs are relatively permanent and thankfully not tied to the CEDAR Madrigal database domain so that we don't have to maintain them. We use a W3ID redirect to keep them relatively permanent, and it's quite a bit more practical and economical for us. So of course here we have the W3ID redirect and the experiment file identifiers that are passed to Madrigal. For any PIs in the audience who would like to get their data into Madrigal, there are two methods available to you. One, you can send us your data directly. Please include documentation and desired summary plots. We can try to automate this process of creating summary plots for you. We will write a loading program, which you will verify, and you can choose to add data in batches or via an automated upload. Alternatively, you could set up your own Madrigal site, which we will help with installation and creation of loading programs, but you get to control when the data is uploaded. And everything that you upload to your site will be automatically backed up to the CEDAR Madrigal site. So onto the main topic here, some needs and challenges that we're thinking about. It would be great to have a consistent input data format for all of the data upload requests that we get, but unfortunately this can be a bit nuanced as the instruments themselves tend to be updated from time to time, change file formats, include new data, etc. So this is something that we would need to work with the PIs for. As far as making the data straightforward and understandable to the user, generally this is handled by the standardization of parameters and metadata, but as Asti mentioned previously, this is just the CEDAR Madrigal standard. But as John Vandergriff mentioned earlier, we would like to be able to get the CEDAR Madrigal metadata format translatable to the HAPI metadata format so that we can interface with that. Being able to log who's accessing the data is very important. We generally don't enforce this too strongly. Access to Madrigal requires a name, an email, and an affiliation, but no password. None of this is verified, but is enforced by browser cookies and arguments in the API. The experiment PIs are given access to the usage logs for their data, but as was previously mentioned earlier regarding cybersecurity, it would be good to have some way to verify that the user is who they are, who they say they are, but to still be able to maintain the whole point of this data repository, which is open science. Everybody should be able to access this data, so just don't misuse it, please. And finally, the most important challenge, or the biggest challenge rather, data size and storage. Data volumes are ever increasing as time goes on, and there are many use cases for these large data sets, including processing data and serving data, which we would like to be able to use the cloud for. Currently, as far as data crunching, we use vSphere to process our TEC data collected by the Millstone Hill ISR. But we would like to also be able to serve data via the cloud. However, I/O is very expensive, and we would like to be able to communicate with other folks who are interested in pooling their resources to maybe create a data or a cloud-based data commons that everyone can access and participate in. And with that, I hope this gets some ideas going and some discussions started for how to further address these needs, some further ideas and thoughts. And of course, thank you so much to everyone for listening, and thank you to NCAR and the organization committee for supporting early career folks and my travel and all sorts of things. So yeah, thank you all for listening. I'll take questions later.
Thank you very much for your presentation. I wish I was that confident when I was early in my career. Fantastic work. Our next speaker is Michael Bell from Colorado State University.
That looks like my old presentation, so, well, we'll go with whatever is on there. There was a new one that I'd sent to Tasia earlier, but hopefully, yeah. Oh, I guess I should have checked it beforehand. Well, I tried to update it because a lot of the things I put in here actually have already been said. And so I'm a data provider and a software provider. I had a slide on here about the CSU CPOL radar. Well, I'll just keep going. So I, as one of the organizers of this workshop, one of the things that I've been thinking about is, what does geoscience data analysis really look like in the future, right? This is one of the things that, and we're not that far removed from printing out paper maps and using that. And so, but we have new technologies now, and so I asked generative AI, what does this look like actually? And I got a lot of images actually. You get a bunch of crazy ones, but this one I think actually is a pretty good one that shows what we can think about for the future. Is equitable, inclusive access to data, new tools of ways to visualize. Things like a hurricane. I would love to have a giant screen like this. I think we could probably ditch the lab coats, but I think our students that are working on this data, they're working on it now, though, right? So we have these new technologies, and they're not going to wait around for us to build this new data commons, but we have to take the things that we're going to do. I have a new summer intern coming on Monday, and so this data commons is a little ways away, but we could take a step back and kind of think about some of these bigger pictures. So in my title, I said uncommon data. So what do I mean by that? Well, uncommon data is, I think, things like field project data. I hesitate to use the word common data for something like NexRad because many countries actually don't have the same level of infrastructure that we do here. But we are pumping out terabytes of data a day from the NexRad. As Kevin said earlier, I think really well, that real-time data is really important, and we use that for a lot of different things. But then we spend a lot of time building new instruments that take years to plan and build and go out and conduct field experiments. So the CSU CPOL radar that I'm the PI on is a NSF community facility, so anyone can write a proposal and request that data. And then I'm also part of the team that's building the new airborne phased array radar here at NCAR, which is going to be producing really massive data volumes in some sense relative to current radar systems, but actually quite small compared to sort of petabytes of data that we're talking about in other contexts. So I want to give just a quick example here. So yeah, you can tell I didn't have some typos in my slide that I fixed from before. But one example is a project that I led back in 2022. This project was called the Prediction of Rainfall Extremes Campaign in the Pacific. This was a multi-national, international field project involving many different U.S. and foreign institutions. This project got its inception back in 2015 when we started talking about this. It was delayed 2 years because of COVID. We were supposed to go in 2020 and then again in 2021 and then finally in 2022. So a lot of people put a lot of time and effort into collecting this data. And we had NCAR SPOL, which is one of the lower atmospheric observing facilities. We were out there for 78 days in the Hsinchu area of Taiwan. We have over 13,000 radar volumes with 176,000 RHIs. That's a vertical slice through the atmosphere. The CSU pole radar was on this very tiny island called Yonaguni Island. That's the last island in the Japanese chain. It operated for 74 days and also has a really remarkable amount of data. Some nice pictures of the two radars from that area. We also had 3 NCAR micropulse-styles. These are LiDARs that produce differential absorption LiDARs that produce every 5 minutes water vapor profiles that operated for 75 days. We have over 1,300 radiosondes launched 4 times daily, in addition to a lot of data from the Taiwan Tahoe program. And so in one sense, this is a lot of data. In another sense, it's actually quite small. But it is uncommon, right? It's not the kind of thing that we're going to get all the time. It takes years of planning. And we want to figure out ways that we can make this data available to the community. And it was said earlier, you know, we want to get the data out there. We want people to use it in the right way. But we want people to do really good science with that. And so one other challenge, though, with international projects is that every single, both institution in the United States and those abroad, each have their own data policies, and we have to also deal with data policies across different institutions and across different countries and different funding agencies and things like that. In fact, okay, oh, actually, now I've got my, okay, now the slides on here are different than the ones on there. All right, thank you. All right. Well, this is good. This is what I wanted to show. So, so that data actually, of course, is all right. I'm going to have to change all this up. All right. It was said yesterday, I think Deepak said it really well. Data is also about people, right? And when we think about data, all the data that's being collected is being collected by lots of different people. And so I've just got a bunch of images here that are being shown from all the different students and researchers that were out in Taiwan and Japan. There's wild horses on Yonaguni Island, too, that sort of indirectly contributed to the project. But we really, it's a team effort, and I think everyone that was involved in this project really wants to see that data become scientific advancements. So, okay, I'm seeing things happening on the screen here. Okay, well, all right. The preset model data, so the observational data is about 20 terabytes, actually. And, okay, sorry. You can't see what's going on right here, but they're doing some magic up in the screen right here so that I can control this again. So, okay. Model data is actually about 200 terabytes in this case. So we actually had 3 different modeling groups. And the NCAR folks that were running the MPAS with a 15-kilometer refined down to 3 kilometers. We had the Penn State WRF group running a 40-member ensemble assimilating all-sky infrared radiance from the Himawari satellite. And then we also had the GFDL teleshield, which was a global model nested down to 1 kilometer. And so despite all of the observational data, in fact, the model data was actually one of the largest things that we collected. And my understanding is that in the RDA, in fact, a lot of the analysis products in the model data is, in fact, one of the largest data sources. So I think we need to be thinking carefully in the Geoscience Data Commons about what kind of data are we talking about? Is it observational data? Is it model data? Is it all of the above? And I probably would argue that it's a bit of all of the above. Okay, now I have control. So I'm going to go back because I actually changed my slides around. And so I want to take a big picture here and then ask, so which aspects of this data pipeline would the Geoscience Data Commons optimally improve? So we could think about, I like what Douglas said yesterday, what's our North Star here? What are we what are our metrics that we guide this project? And, a lot of us may think of a sort of a pipeline like this, where we go out and we collect some observations, we do some sort of analysis or data assimilation to produce some sort of state or analysis, and then we run that through conceptual numerical models, ML or AI, improve our conceptual understanding, and we can use that understanding to do hypothesis testing and verify against those observations. And so I think a data commons could actually help with many of these different things, but we need to think carefully about which aspects are we going to target, because we can't do everything all the time. But I want to flip it around, actually, and I can say, we can actually sort of reverse this, and we can say, well, is it more data that we need, or is it better data? And I would argue that really what we want to do with the data commons is think about better data. Now, there's lots of different ways we can value that in terms of what is better. But we could think about better data as, for example, reducing observational uncertainty. We're going out and targeting observations that we didn't have before, for example, with field campaigns or with new sensors that people are developing. That reduced observational uncertainty can lead to better conceptual models. That can help us reduce process uncertainty. That's a really fundamental thing in all of our models and our understanding. If we reduce that process uncertainty, we can use our computing power more efficiently. So we can put that computing power where we need it. We don't necessarily have to increase the resolution of everything. There are certain things we don't need to simulate better. But right now we don't know what a lot of that is. And that can actually reduce the uncertainty in the state of the atmosphere, which then can help us determine what kind of data we need in the future. So I think this can be a nice virtuous cycle that this geoscience data can solve. So the other point that I had on this slide was just that this is much smaller volume than operational data, but it really is unique and important to reduce uncertainties and solve scientific problems. So just a quick a few points then. For the precip, when we talk about data, we're really talking about data at different levels. So we came up with 4 different levels for our project, 0 being raw data in its native instrument format. That's in these complicated, compact binary formats. Kevin said earlier, transmission formats versus storage formats. If you convert the data into something good, like NetCDF, for example, or another type of format, we called that level 1, but there was no processing applied, just into a better, or at least a more convenient format, I'd say. Then we said level 2 is actually QC'd measurement data. So no additional science applied, but what's the best possible measurement from this instrument? And then level 3 would be what we call analysis data. That includes value-added products that require some kind of scientific decision making. I think that's an important distinction to make, because different people are going to make different distinctions. But that decision making requires domain expertise. You can't just go in and just grab a bunch of radar data. So for those of you that aren't radar people, if you're looking at this on the right-hand side, that's the level 2 data. Most people aren't, that's not very useful for them, right, if you don't have that domain expertise. But these levels are defined differently depending on the different providers. So we have to be really careful about how we use these levels. I already mentioned that this is about 20 terabytes of data for just the level 3 data, but we have multiple versions of the data we have to deal with. And then, so questions for the breakouts potentially: how much processing should be the responsibility of the data provider versus the user? How do we educate users on these different processing levels? How do we avoid redundant storage, processing, and analysis so we don't have multiple copies of the same thing floating around? And this was brought up earlier by Asti. How do we communicate updates about the data? So when we find problems, we have to let people know. And if people didn't register, or if there's no communication pipeline there, then then they're using the wrong data, and they may be publishing something with errors in it. So then I'll end with a few slides here. So this is also some AI generated. So I have 20 terabytes of data. Do I just take that and dump it into the petabyte C? I think that's not what we want as data providers, right? We don't want this just to go into some big giant archive. What I envision is the future is I say, hey Siri, hopefully my watch doesn't hear me, Alexa, ChatGPT, whatever data provider you want, what data is available to study the problem I'm interested to solve? Okay, yeah, okay, I figured that would happen. Help uncommon data providers. So one way we can do this is, I think, helping smaller data providers improve their metadata so it can be effectively discovered by users. An instrument builder may know a lot about how to build an instrument, but not how to actually, make it available. And that's where I think a lot of the expertise in this room is helpful. And then I really like the idea that's been floated of large language model with standardized metadata, just asking for data, right? Then access, we have, the processing level applied depends on the user and their expertise. My summer student coming on Monday is going to have very different needs than a postdoctoral researcher. So we need to think about users across that scale. And I think that the domain expertise needs to be integrated in this pipeline, especially as transdisciplinary and interdisciplinary science increases. People are doing a lot of work, for example, in health and weather. And I know some of my colleagues in the health department, they're just downloading weather data and they don't really fully understand it. And they're using it, though, because they have to solve their problems, right? But they're not necessarily going to go and find me and email me about my data. They're going to want to find something on the web. So we need documentation and citation of the collection methods and the processing applied, appropriate scope and volume of request. Don't serve up petabytes when kilobytes will do. And then the platforms and software tools that go with that analysis. So on the right here is, for example, some level 3 data from the CPOL radar. And but what people might want is something like this, which is hydrometeor identification. And so one of the things that we've been working on is how do we help view, analyze, and understand this data? And we've been working on the LROS Science Gateway, which is a Jupyter notebook running on Jetstream 2 with a Kubernetes cluster. We've already had a lot of talk about these notebooks in the cloud, and we had some really good discussion in our breakout earlier. People searching for workflows rather than data, right? So finding the workflow. I want to calculate a rain rate, and then that domain expertise comes along with the data. Right, so someone's already planned that out, and they know, and that's for both research and education. I used this in my classroom recently, actually. But there's a trust here in the scientific results through documentation, testing, and maintenance is really critical. So just to summarize, because I know I'm already over, sorry for the technical difficulties there, data volume and complexity will continue to increase. Same for better data access, not just more data. Documentation and the processing need to be tightly integrated with the data itself. Standards are essential, but they often are domain specific and will continue to evolve. I think the radar community is one where we've had a lot of success with CF Radial working together with DOE and other groups to work on common software tools that rely on a common metadata. And in fact, that now CF Radial 2 version 2 has been adopted as the new WMO standard for radar data, in part due to those efforts. So I'll leave these closing thoughts up. Trusted workflows are essential. We shouldn't have to reinvent the wheel, but we need ongoing resources for maintenance support. Data analysis is not sausage making. It requires critical thinking. You can't take the data and just put it in a grinder. And incentives are important. How do we best incentivize contributing uncommon data and value-added products for the community? Thank you.
Perfect. No. See, that's the difference between the testing. That's the difference between the way we treat our early career and our more senior scientists. We mess with their slides. But I got to try that SIRI hack one day with an audience. That's very good. Our final speaker for the session is Douglas Rao from the North Carolina Institute for Climate Science Studies, not science. I nearly said science. Awesome. And you're going to use the lapel. No. Do we have the lapel?
Okay. There we go. Right. As the last presentation of the entire workshop, and so I feel a lot of pressure on me. So a little bit about myself, floating between university and a data center at NOAA. So I am with the North Carolina Institute for Climate Studies, also with the Corporate Institute for Satellite and Earth System Studies within the North Carolina State University, also working with Rob and Eric, who are both here, NOAA's National Centers for Environmental Information, as well as NOAA Center for AI. So I have seen both worlds. When with the university, I often being asked by departments, researchers, and students about what data they can use or how they can use those data. And then on the other side, with the data centers, what we often ask is that who are our users, and then what do they need about those data sets. So I kind of play the friendly ghost in the between space. And when I was making this presentation as the last one, I was thinking about what data commons really means. And then I think a lot of discussion happened today and yesterday can be summarized with the title of a movie that comes up next. It's like we want everything, everywhere, all at once, right? From the data to the compute to the educational materials and the users all at the same place. Well, now I'm gonna go through a storytelling exercise with everyone to figure out like how can we really get there, or can we actually get there?
So my friends sometimes accuse me work for AGU because I use a lot of AGU materials in my presentation. So this is one of the materials I steal from AGU Sharing Science program, looking at how can you do a storytelling with your science communication. Like obviously we start with a beginning of the story and then try to climb to the climax and then get into a place where we have a hopefully happy ending for everyone except the villains. So let's think about with data commons or data analysis of the users, what usually that happens. So once upon a time, and we want to study certain subjects, like insert the subject of your interest here, whether it's using a data set for emergency evacuation or for like study of the fundamental physics of the Earth systems. And then as a data center, it's like, oh yeah, we have the data, come to use it. But when the journey starts, you have the access barriers, you have the quality of the data barriers, you have the integration of different data. How there's nearly any use case now we can just use one specific data set can solve everything for everyone, right? So you need to integrate data from different sources, from different like observation or from models and trying to adjust that. And then climaxing this story is like, what about data science? Like what about machine learning? Everyone's want to like throw data science in the proposal these days. And when I was reviewing, like 75% of the proposals I've been reviewing these days are machine learning focused proposals where I'm trying to address some issues. And how can we really get where we want as a data commons and trying to address those issues? I really like the comment that Michael mentioned earlier. Is like there's no magical user. There's more than just one type of users, right? From the people who are in the field doing those emergency response, and for the people who are in the lab doing the research with the models as well as the observations, those are totally different type of users. And how can we really address all the needs from them, or there's any spaces for other people to be a part of that process? So we are here today, and like we have talked about other things like fair data principles that have been mentioned on the first day, that this thing has existed for 10 years now. It was started in 2014. Now we're still talking about fair principles and how can we use that in a most efficient ways. And then there's analysis-ready data, like USGS published their analysis-ready data for the Landsat that kind of like pushed a lot of the Earth observations trying to think about what ARD means for the Earth observations. And then there's the cloud. You cannot mention Pangeo and all the Pangeo community and analysis-ready cloud-optimized data, right? And this has been thrown darts like just this morning, AI or machine learning ready data sets. And then that has been something we have been thinking about from the NOAA and others, different groups, and thinking about what AI machine learning ready data really means. And now we're here, and we are looking towards the data commons into the future, and thinking about more like technical, I guess from PPT PowerPoints to like Google Slides doesn't really work well with all those texts and formatting. For the technical side, we're thinking about access to the data, to the provenance about the data, especially from operational data centers or the agencies. Provenance is one of the things that we always think about, especially when people are using those data, when there are multiple versions of the data floating around, and when somebody touched that data, and then there's a risk involved in it, and what's the provenance. And European Space Agency have been thinking about blockchains to do a verification of those data, whether those are like really the original or the right data for people to use. And the standards, we all talk about standards like today, but we all hate standards. We all hate the new standards that have been imposed on the data centers when we're talking about the new developments. And then also tools to help people to use those data. And there's also the non-technical side, right? There's the documentation and then how to help users use those data, and what are the services, data services can be provided, and the support. Really, we're talking a lot about the support. I mean, the ECMWF's presentation thinking about how all those like thousands of requests, and then how can you really support all different types of users to use those data, and especially thinking about sustainability of all those services being provided and information provided through the data commons. And there are a lot of things that only a few listed here. So driving a little bit back to the topic that I have been thinking a lot with some colleagues is the AI-ready data. And like this is a slide we often use
one of our opening slides when we're talking about AI-ready, especially when a lot of agencies or different organizations are thinking about moving into the data science or AI sphere. It's really we need to find the right source of data, organize data, and feed the right kind of data into the models for those AI development processes. And however, like David John mentioned earlier, like what is really AI-ready data? And there are different aspects of it from the UK's national AI strategy. It's general, like fit for purpose, and what does that mean? And then recorded in standardized formats. And also they especially mentioned about future-proof, right? You're talking about a system that can stand against time, which is something we can spend an entire workshop about what future-proof system means. And like there are different dimensions towards this definition of or discussion about what AI-ready data means, like from different modeling techniques to the use cases and to different types of data we're dealing with. And in a recent community survey that we did for about 100 practitioners, looking at more than half of those practitioners really using those environmental data in their AI or data science pipelines, spend at least half of their time in the effort to preparing the data for their specific. We always heard those statements about 80% of the data scientists' time is spent on data cleaning. Well, now this is specifically for environmental data. We did a survey for about 100 people. And then one of the creators for the carriers said that really preparing data is important, but it's left to the users to decide how they want to do it, right? We don't want to touch it from the software package point of view. So let's just let other people deal with that at that point. And so there are some discussions yesterday was talking about, don't we already have some communities out there? So for data science, earth science data, or ESIP, the Earth Science Information Partners, is one of the community really thinking about how we bring people together from different groups like the university, industry as well as agencies to talk about the advancement of the informatics in earth science. So within ESIP, there's a group called Data Readiness Cluster that I'm involved in, and we are thinking about different aspects of AI-ready data, from the data access to data quality to documentation, then how you prepare those data, where documentation is to increase data usability, to providing those relevant information easy to use, including the modernizing the data documentation. And then for the quality, is really being asked by many people to determine whether this data set is fit for purpose for their use cases. And also the access is really increase the efficiency and the reproducibility. And for preparation, is really identifying the common patterns of how those data is used being in those data science applications. So there's GitHub if you want to learn more about different aspects of those, and you can go through the checklist directly. So now I'm given the time. We already started late today, so I'm just gonna, okay. And so for the, one highlighting some of the things we're talking about. So for documentation, when we're talking about modernizing documentation, Jupyter Hub or Jupyter Labs or Jupyter Notebooks have been mentioned multiple times. And then when we're talking with people, they always say providing sample codes and those workflows in the Jupyter Notebook provides much friendly way to help people to use, rather than having a 50-page of documentation there trying to figure out what's the quality of this data sets and then how people can use it, right? And then for the access, a few people already mentioned in the presentation, as well as discussions, that people prefer different variety of formats. And although as much as we hope that there's a one data format that rule it all, it's not going to come, at least not in the next 5 years. If we can get there in 5 years, that would be wonderful. And then for the preparations, really a lot of the ask has been the labeled data, and then the outliers being identified, and how, especially in the data science applications, oftentimes how to split those data in the right ways. When you're reviewing papers in machine learning applications, you often see how people are misusing those data by splitting it in the wrong ways, and then trying to have those spill effects into the validation that it's hard to see, but you still see those papers being published. And so how can we provide those right information to help people to use it in the right way? So I'm going to use one specific example, trying to address some issues with those orphan or legacy data sets, the old versus new. One of the data sets that NCAR put out is the climate data records that It's updated regularly. Some data sets updated daily, some data sets updated quarterly for those climate applications. So there are about 40 data sets from the fundamental CDRs, fundamental climate data records, which are the brightness, temperatures, radiances from the satellite sensors, to the thematic CDRs, which are atmospheric, oceanic, and terrestrial like CDRs, where those data sets have been put through all three cloud service providers on Google, Amazon, and Microsoft Azure. And when we think about those data sets, that data set was like defined and produced, started in the 2010, right? So that's 14-year-old algorithms and product requirements, and everything. You all have the ATBD as a documentation describing what data set is, how the model is developed, and then what's the quality of those data sets. So here, looking at those like specific one data sets, we're looking at as a leaf area index for the ecosystem like research, right? There's opening up that NetCDF files, and there's no mention about chunking, right? It's the daily file in one chunk at 0.05 degrees. So if you try to look at daily data for this like 45 years records, if you only want to look at the city of Boulder, that is going to take you forever trying to open up all those files and then extracting those time series for analysis. Another example is that for the quality flag defined 14 years ago, that is a bit-based quality flag. You're trying to figure out which pixel I should use in that based on the high quality, whether there's a cloud, whether there's no cloud, whether like vegetation types are including it, and who, for a lot of people, the users often, the most commonly asked question by the users like, how do we decipher this quality flag? And that is, we got emails, if not daily, it will be at least weekly about how to do that. So really it's the mismatch between those like products and the product requirement defined in the 2010 or before that, and then in the new technologies that have been evolved since then. And how do you like bridging those gaps in a way to make everyone's life easier? I'm sure nobody wants to keep answering the same email about how can you read in quality flags in the data center for specific things. So when we're thinking about the four different aspects of the preparation, the area-ready data, it's really like for the access modernization, really a lot of people are talking about the cloud and the cloud native like formats and how can we adapt to those access technologies and balancing the needs for the archive and stewardship, especially there are a lot of data sets that have a retention policies. If you know what that means, is that a lot of data sets is like required to be kept by the data archives for a certain amount of time or until a new version of the data being released, right? So you cannot really legally get rid of them if it's in your archive in that sense. And then there's also the data service part is really how can we provide the data service that commonly requested, right? Understand the user's needs and then design the service that to meet those users' needs. And for the capacity development that had been mentioned so many times throughout the entire discussion like this week is really providing the training, capacity building, and also updating the some outdated education like curriculums that it doesn't really fit the current landscape anymore. And really for the quality, going back to especially for those like older data sets, we shouldn't really try to rely on documentation and figure out people knows how to read the documentation for finding the right data. And also, commons, when you have access to more than 3 dozens of sea surface temperature, how do you know which one sea surface temperature should you use in your research, especially for the people who are non-traditional earth scientists, right? When they come from energy sector, they want to use the SST or whatever data set can meet their users' needs, like what is the right one for them to use. So I have to brag some of the projects and the things that like associated with my paycheck. So one of the data that I'm thinking about, especially with the data integrations, right? There are different sources of data from observations to model simulations and to satellite observations. So some pilot projects NOAA Center for AI was working on with the CIRA teams there. It's looking at the how integrating the observation and from the
the best tracks as well as the satellite observations from thermal infrared as well as the microwave data and the ERA5, trying to create a data set that can be really specific for the tropical cyclone research, right? So that's kind of more specific AI-ready data set for a specific use case. But when we talk more broadly about AI-ready data, it's really finding the common practice where from a data center or data provider point of view that we can get to there where reduce the efforts by the users as much as possible, but they still have the last mile problems for the data delivery and data services. That's where other parts can come in, the software engineering and then the tooling that can bridge in those gaps in that specifically. So there's also some ongoing industry involvement in related to this specific things. That it's my last slide. I saw like Scott stand up. It's Croissant, which is really a high-level metadata for those machine learning ready data sets, and that really figuring out that integrating from the data creators to data repositories and data users, right? This is actually driven by like Google side, where they have a Google dataset search and other things, and then they're trying to figure out like, can we help like maximize or like operationalize some of the search of those machine learning and training data sets. So this Croissant format came up and then has been integrated into the Kaggle, Hugging Face, and OpenML, like where you can search all those with a Croissant metadata formats, and then you can also directly integrate into the data workflows in the in TensorFlow as well, PyTorch, JAX, or Keras, right? So that is an entire ecosystem. How can you integrate and make the people's life easier through some technology developments? With that, I'm gonna stop here, and I think we have brief discussion happening.
Awesome. If I could get all of our speakers up the front, and is our speaker still online? Are we able to bring her up as well? Awesome. Just a comment from the moderator as well. ARM also uses Bitpack QC, and I think it's a perfect example of something that some software engineers thought was really, really clever, but not really thinking about the user experience at all.
It comes from maybe 10 or like 15 years ago because the storage is the issue, right?
Exactly.
You want to reduce the file size as much as possible that when you resolve into that way of doing the QC.
Questions for our panel? Yes.
So I'll kick off with a fun one since you just showed the slide. Is there anything in AI-ready data sets that is relevant to AI? I mean, it looked like it was all good data sets. I mean, is there anything AI specific, or is just the evolution of what best practices look like?
I agree with you. We use that way as a way to modernizing, because the title of my presentation is really to modernizing data management. And a lot of things like quality is the information that we see being asked mostly when we're doing the survey and when we're talking with people. It's like trying to find the right data set for them to use.
Maybe calling it AI is just the way to trick people to pay for it.
I cannot comment on that.
Anyone else want to comment? Wait, we've got another question up the back here as well. I'm going to get my steps in.
An open question just for anyone. Compression, as a data curator, sometimes people send me .NET-CDF files. I ask them if they could compress their many, many terabytes of data, and then they send it back to me in .nc, .tar, .gz, which kills me a bit inside because they don't know how to compress their files natively in NetCDF. So, I mean, either with the Madrigal database, where people are sending their own files, formats, who should be responsible for compression? Because, like we've heard many times, we can't store petabytes, exabytes of data forever. Yeah.
So generally, it depends on the type of data that's being sent over. I'm just now foraging into the world of big data as far as Madrigal is concerned, and of course, compression is a huge consideration. The data being stored in HDF5 does help with compression. But going forward, especially as data sets continue to get larger, I think this is something that we'll just have to think about more. So.
If I can comment on that, I think. Sorry, I'm the biggest one here.
Just gotta get out of the way there. Yeah.
Oh, sorry. The raw data that we store in many of the instruments, raw data have their own value. They are compressed, great, but even if they are not compressed, I think we as a broader science community, science computational people community, we need to find a way to store them. And NSF probably needs to support that in some sort of centralized way. I don't think we can, I hear your frustration, but I think the solution has to be bigger than individual curators or data providers.
Yeah, so from like the model data and even observation-based data sets that are derived from like fundamental observations, I would like to learn more and have more guidance on lossy compression, because it really doesn't matter if your grid cell is 258.888 repeating Kelvin or 258.8. You know, for almost all applications, you don't need that precision, and it's honestly completely unwarranted as well, right? It gives a false sense of security or whatever. So I would be happy like to take that on the provider side, but I would want the support to like know which algorithms are out there, how to use them, right? Because then we can decide, do we need 2 bits, 3 bits, or whatever of precision given the variable.
And I'll just add one other comment about that is, I mean, we also need to think about, in terms of that compression, you mentioned, the .tar, .gz, but if you have data that's coming out, for example, every 5 minutes or even faster than that, we don't necessarily want to serve up, thousands of files either. So we have to think about, what's the granularity of the data requests that are appropriate. And part of that's a technological challenge, but I think that's also partly gets back to my point about the scope and the volume. A lot of people don't necessarily know what they want to request. They're going to request more than they probably need in general. So, because they said, just give me all of it. But that's not really what most people actually really need or want. So I think it's a two-way street. So thanks.
Thanks. Yeah, this is just a comment on Asti's talk. You had a slide at the end about learning where you had a set of points from the data facility perspective. And I just wanted to say 100% yes as a data facility person to everything you said. Like the challenges of providing consistent, continuous access to, fair data with limited resources, the skilled labor it takes for the software data server maintenance, that ML-ready data sets are a new challenge, a new expectation that we have, and we would also love to outsource the sort of data storage, versioning, DOI machinery, and focus on what we know, which is the domain data. So thank you for that talk.
Thank you.
But there's something that goes straight in the report. And sorry, we've got a bit of a queue going here, but I saw one hand up there. So you're after Max, who's after this guy.
Yeah, I need for Ken. Yeah, the last slide, you mentioned that the hurricanes or tropical cyclone data from NOAA and Sierra. Is it aircraft data or the satellite? Who archives that data? You should.
So the data is right now made available through NOAA Open Data Dissemination Program on AWS, as well as in the process being archived by NOAA and NCAR, so in the data archive, which combines operational satellite observations as well as the environmental conditions from ERA5, the area analysis. So there, if you are specifically interested in that data sets, you can reach out to Chris Slocum from NOAA and we also have the notebooks on teaching you how to use those data. And there's 8 different notebooks on introducing data formats to how to use that train basic model in machine learning.
Thank you.
Perfect. That was easy.
Yeah, I just want to add one little quick comment because the student that made that database is my PhD student, Nafal Razin, and that data started as actually sort of an internal thing that we wanted to do for his own research, and then we realized that it was going to be something bigger and better. But then we had to work with NOAA, and that's what I was talking about in terms of incentives and value-added products. Is once you've done something kind of cool, we need to figure out ways to make sure that people can give that back. And so now Nafal is doing that for his postdoctoral work and working with Douglas. So it's just super exciting to see that. And so also, if you have questions about TC Prime, you can ask me too. So yeah.
So how do you balance the ease of use of, say, somebody going on and accessing some data set without authentication or without some sort of user having that sort of metric, balanced with being able to send messages to users when there's bad data? Say, for example, some surface station, there's a bad METAR decoding where all of a sudden it's like 1,000 degrees Fahrenheit. Like how do you balance the ease of access and being able to notify users?
Depends on what side of the bed I wake up on. I used to be a very, very big proponent of I need to know every single person that. I even went so far as like creating my own email lists, right, to communicate when there was an update. And then some days I'm kind of subscribed to more like the Copernicus journals, right? If you submit to like ESSD, right, I think it's all anonymous, and so it's very hard to know anything. So like maybe that's too far some days. Yeah, I don't know.
I don't think there's a perfect solution, but I mean, with a CMIP, right, they have the errata service, right? You put in the information about whether those variables are right or wrong, and whether modeling center want to address it or not, based on the resource they have and how critical those things are. And I think if that service exists, then it's really the promoting and educating the users to go to that places, right? Rather than, because their agencies just don't want to collecting those information because there's privacy concerns and other things about that.
So we don't actually do that. Most of our data users are, well, we don't know how they are downloading. There is no authentication that requires. So we focused on trying to provide data quality matrix as part of the data, errors as part of the data, and really using conferences to shout from wherever we can find to say, please contact us before you go ahead and publish something, and walk the halls at AGU, poster halls at AGU, and find people who are showing data from your instruments, but you have no idea that they're using it like that.
Yeah, can you all comment on any tiers of access you've created for the data you're providing access to, like for different tiers of access for previous versions of data, or levels, level 0 data versus level 4 data? Because presumably it doesn't all need to be provided the same level of access, but it's all important.
Yeah, well, in the field project case, usually we provide the different tiers of access to the PIs. So we'll provide, and I think it gets back to sort of short-term, medium-term, and long-term pieces that was talked about in some of our previous work. So in the early stages, we want to provide more access to the raw data, and then as time goes on, more of that. Everything that we're doing in our case is all supported by NSF. So ultimately, it needs to be public data. But there is a sort of a preliminary period where just the PIs or whoever is collecting the data has access, and we iterate with them. So it was mentioned a bit earlier about embargoes. So there are different levels of access at different time periods. And I also mentioned data policies. That's going to depend on the project and the PIs and whether you're working with different agencies, things like that. So I think it is very case specific, but I think that is a really important comment. That's something we need to address as part of this, because we don't want to serve up 4 different versions of the data. It gets back to the prior question, so someone grabs the wrong tier of data, then, like, oh, and I think it was mentioned earlier about, for example, also with software, it's kind of the same thing. So, someone clones a GitHub repository, and then we find bugs in it. I mean, we update that, but then there's no good way to go out and say, everybody that's cloned this repository, how do we notify them? So, I think it's, some of it's contingent on the user, but we need good broadcast mechanisms as well. So,
Thank you so much. Really great presentations today. So my question is about this decision on moving to commercial cloud, especially with the considerations around egress costs. From my understanding, egress costs are going to be waived for a limited number of years, 2 years or 3 years. And then after that, no one needs to pay, or like the user needs to pay for the download, or that's like maybe I didn't understand it correctly. So if you want to build some infrastructure that will stay around for a longer term, what would be the most sustainable way forward? Would it be, yeah. And again, I don't understand all those politics around all the policies and yeah.
I'm not sure I'm qualified to answer that question, but at least right now, and all the data you use, like from NOAA is like free, right? There's no egress. I know I was looking at Jed, like he was nodding the head because he was with AWS Open Data Program at the time when NOAA started experimenting with commercial clouds. That's what used to be called Big Data Program, and now it's called NOAA Open Data Dissemination Program with like 10-year contract with all three cloud service providers where no fee was charged accessing those data, at least for now.
Perfect. Can we thank the panel once again? So we're going to go into our coffee break now. Breakouts will start at 3:35. Do we need to put up the put up the assignments there? Remember, once again, 680B is a restricted access area, so make sure you find your host to go to that one. And we'll see you back here for the debrief.
All right, thanks everybody for reconvening. I just wanted to remind everybody to please put suggestions on the Slido for potential topics tomorrow for the breakout and upvote those that you find of interest. So there's the link to this. Go ahead and add things after this is done overnight to your upvote, and then we'll have a final opportunity to do upvote. Do you have a question?
Are we doing one topic for all the breakouts, or are we going to have a couple different topics?
What do people think? And we can, if there are two that are pretty close, we can make that decision tomorrow, I think. But I'm open to whatever people want to do. So, different, multiple topics. Okay, multiple topics it is. Anyway, upvote the multiple topics you want to discuss, and maybe we'll have enough breakouts that they'll all be discussed. We'll see. And then we're going to make a change in our schedule. We're not going to do report outs right now. We'll go through them in the morning before we start. And we'd like to take a group photo if people are open to that, and then we'll close out. So we're going to go stand kind of in front of an orange mural out there on the wall, and that's where Tasia wants to have us. Okay. Yeah, go ahead, Deepak. That happens a lot, yeah. All right, so the Southern Sun is, you can look it up on Google, but it's just at the bottom of the hill at Broadway and Table Mesa in that shopping center. There's something called Under the Sun that you can see from there. It's above that. Cash or check? So I actually bring one check in my wallet when I go to the Southern Sun. Yeah, because I don't use a check, but if I go there, you're getting a check. Okay, well, let's go ahead and go out. Do you have any more announcements?
The shuttle leaves at 5:30. Don't forget. So.
Oh, and then we have the HBCU folks. We have a 5 o'clock. I think. Well, we're going to try to make it upstairs for 5 o'clock.
Follow Egg Belly if you're part of that group. Anyway, okay, let's head on out. Do the picture.